Hello everyone, my name is Shambhavi. Hope you all are doing well. Now today we are going to see about the data. In the previous video we had already seen that what we meant from data, right? That what is this data and what we meant from it. Now today we'll be categorizing the data into particular two parts. Till now we had only understood one single term, that is data, right? Now today we'll be further categorizing it into the two forms and then dealing with this particular thing. So the first thing that I would be describing here is qualitative data. Qualitative data. And the second one basically which we have here is quantitative. So these are the two types of data actually which we are having. This qualitative and quantitative is basically subcategorized, but that will be not discussing right now in this particular video, right? I will be discussing about the qualitative and the quantitative. Only and only these two terms. In previous video, actually once I had taken a name for both of these names. I just taken out both of these names actually in one of my previous videos, that was qualitative and quantitative. There I told you that we'll be discussing about both of them detailed in this further video. So here is a particular video in which we'll be discussing about the qualitative and quantitative. Let's not waste too much of time in this discussion. Let's get started. Okay, let's see about that what we just meant from qualitative data first of all. Okay, let's see that what we meant from qualitative data. So the data, okay, I would just write out a definition as well here. So the results of categorizing, categorizing, okay, G-O-R-I-Z-I-N-G, fine. So the results of categorizing attributes of a population. Categorizing, or we can just give it as another name, or describing as well, we can just say out, okay, or describing, fine. The result of categorizing or describing attributes of a population, that is attributes of let me come down and write it out here, attributes of a population. So qualitative data is the results of categorizing or describing attributes of a population. Now, what are the examples that comes in the qualitative? Let's say I just talk about a person. Okay. The hair color of a person, the blood group of that person, what is the blood type, what is the car that person is driving, and basically what is the street, what is the place where that person lives. These are all the examples of the qualitative data. Okay, so qualitative data is a kind of data which is actually described by the characters, by the words or by the letters. In the previous video, we had discussed about the numerical and the categorical, remember? So what was numerical doing? Categorical. Categorical were the data which was having characters. That categorical data was always having characters. Same thing in the qualitative as well. So the qualitative data is generally described by having the words or letters. So wherever you just find out words or letters in any particular data, you would quickly call that, okay, this is basically a qualitative data. Fine. Now, when I mentioned that the hair color, the blood type, basically the car a person is driving, the street a person lives, and these are all the examples of qualitative data. So what are these all having? These are all having the answers in the form of words or characters. If I talk about hair color, so hair color can be black, it can be dark brown, light brown, and blonde, grey, whatever it can be actually, right? What could be the blood type? Blood type can be AB plus, O negative, B positive, whatever it can be, right? In the terms it can be. So this is what is called as a qualitative data. Hope you just got the definition for the qualitative data. Fine. Now let's talk about the quantitative data, that what we just want. Even like from the word only, you can just see quantitative. Quantitative is actually having a word which is quantity, and quantity is always measured in the number. So the data, the results of basically the data which are in the counting or measuring of something, that is actually quantitative data. So I would just write that definition here. The results of counting, or measuring. The results of counting or measuring the attributes of a population. So are the attributes of a population. So whenever we just talk about counting or measuring something, so in that case quantitative comes. Even from the quantitative, if you separate out both of these words, that is quantity and tative. So quantity is basically something which is always in numbers. Quantity is something which we measure, right? That is something which we count. Like let's say I say that I'm having 10 number of pens. 10 pens I'm having. So what is that? The quantity for that pen is 10, and that will always be in the numerical only, right? So that is what we call as quantitative data. When I talk about qualitative, so qualitative is actually having two words, quality and the tative. So quality is what? Quality is always described in terms, right? If I say that you are having black here, so what are the quality of hair you are having? That is the black color, right? So that is always described in the categorical, that is in the characters or in the words only. So from this particular thing, you can actually define that qualitative data is actually having the quality, and quality is always described in the words, and quantitative data is actually having the quantity, and quantity is always described in the numbers, right? So these are the two things. Example for quantitative: amount of money, pulse rate, weight, number of people living in your house, right? These are all the examples which you are having of the quantitative data, because these are the things which can be measured, which is having some quantity. If I talk about amount of money, so that is some quantity which you are having, this particular amount of money. If I'm talking about weight, so what is a particular weight which you are, what is your weight actually? So that is as well some quantity which we are having, right? Hope you just got out the very much clear data regarding the qualitative and quantitative. Now, the quantitative data is further described as discrete or continuous. So, quantitative is basically dealing with the numbers, right? So, that is further described in the discrete or continuous, but that will be seen in the next video. Fine. So, hope you just first of all got out the very much clear difference, because this is the place where people lack a little bit. They are not like able to clarify about the qualitative or quantitative in a proper way. So, hope you just got out the idea that how you can remember what is qualitative, what is quantitative, and what are the particular definitions for both of these particular words. We are having subcategories which are basically discrete or continuous. So let's discuss about that discrete or continuous today. So that discrete and continuous come into the quantitative. Qualitative one does not have, it basically do not have any of the subcategories, but yeah, quantitative one actually has subcategories into it. Let me take out a color here, and I would just write here quantitative, okay, and two subcategories. First one is basically my discrete, and second one is basically my continuous. Okay, so these are the two subcategories which we are actually having out. Right, now let's see that basically what are discrete and what are continuous. So basically what are the data are the result of counting, that are called as quantitative discrete data. Let me write out all data that are result of counting, all the data that are result of counting are called let me write that, are called that is quantitative discrete data. Okay, that is quantitative discrete. So here goes the discrete data. Fine, this is what the quantitative discrete data is. So all the data that are the results of counting are actually called out the quantitative discrete data. Now let's see some examples of the data. Like we can just take out the example that the data that contains some numerical values. Let's say you just count out the number of phone calls you receive for each day of a week. Okay, let's say you just want to count out the like the phone calls which you received out for each day of a week. Okay, so that can be you can just have let's say either 1, 2, 3, or even you can just have 0 calls also, right? So that is the data which is the result of counting, right? So as I just told you the example, let me just repeat that example once again. So let's say you count out the number of phone calls which you are getting in a particular day. right? So that phone yeah, each day of a week. So that phone calls which you are actually having out here, this is an example of a discrete data. Fine, got the idea. Now let's see about the basically continuous one. So I will just write here the definition. All data that are that are the result of measuring, or data that are the result of measuring are called as quantitative continuous data, are called as quantitative continuous data. Fine. So this is the continuous data, that all data that are result of measuring are called as quantitative continuous data. Fine. So example, we can just say that let's say just want to measure out the angle in the radians. So that can be pi by 3, pi by 6, pi by 2, pi 3, pi by 4, whatever it can be, right? So that is basically a continuous type of data, right? That is a quantitative continuous data, right? Okay, so this was about the qualitative discrete data, and the quantitative discrete data and quantitative continuous data, right? These were the two terms that we are discussing all out. Okay, let me just give an example for the continuous one. One more, that let's say you and your friends are having the carry backpacks, okay, and basically inside that you are having the books for the school. So number of books which are actually in that backpacks are the discrete one, okay, and the weight of that particular bag is the continuous, right? So discrete one is basically a count, and continuous one is basically the measuring. So when I just took out the example for total number of books which you are having into the backpack, so that is a count, right? So that is actually the discrete data, because discrete is basically wherever we just put out the count one, that is the discrete. But what about the continuous? So when I just talk about a weight of that particular backpack, so that is my continuous data. So in that basically I'm just measuring out something, so that is actually the continuous. Great, hope you just got the idea regarding this quantitative discrete data and quantitative continuous data, right? So hope you're just very much clear regarding this two subfields of the quantitative data. Now in the next video, we'll be starting out some new topic, right? So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So as we have discussed in the previous video regarding the matched or the paired samples, today we are going to see one question regarding this particular topic, right? So the question which I had actually taken out here, it says that a study was conducted to investigate the effectiveness of that is hypnotism in reducing pain. Okay, results for randomly selected subjects are shown in the table. This table which you are actually able to see out here, this is the table which it is actually talking about. After that are shown in the table. After that, the before value is matched to an after value, and the differences are calculated. The differences have out a normal distribution. So the problem is that basically are the sensory measurements on average lower after hypnotism, or basically test at a 5% significance level. Fine. So this is the question which we need to solve out here. Basically, first of all, I just hope that testing out at a 5% significance level, you must be able to do now this thing onto your own, because really we had done a lot of things regarding testing out a significance level, right? We had seen some things regarding the 1% significance, and even once we had just done out this 5% significance as well, right? Okay, so let's get started and solve out this particular question. So what I would just do here is that I would be writing out the particular things. Okay, just 1 second. Okay, right here. So fine. And okay, what I am giving this table. Fine. So first of all, what I'll be doing is that I would be calculating out the difference. So how we calculate the difference? I already mentioned that it is a data. So difference is basically calculated regarding the first of all after minus before. So after minus before. From this particular thing, we calculate out the difference. So I would just write difference is equal to after minus before. Okay. Let me take out a color from here so that we can start writing the other things. And let me now make out a box as well. First of all, let me move down. Yeah, because this much space you will be needing for making out the table, because yeah, table is a little bit large, right? So like this, the table could actually be made out. Yes, this is absolutely okay. After that, we could just divide this thing into the three parts, because first one would actually be having the upper, before, after, and the difference as well, right? Now let me just again took out some another line from here, and okay, just 1 second. Draw, and here comes the line, and okay, why it is not getting selected right here? Fine. So let's come down again. Okay, just give me 1 second. This I would just remove this out, and again take out a line from here, and find just 1 second. Come down now. So this line would be made up till this particular place. Okay, now let's get started with the things. So first of all, we'll be writing all the after values, then we'll be writing out the before, and then at last we'll be writing out the difference. So this one is for the after, this one is for the before, and this one is basically for the difference. Okay, so let's see that what the after values. See, after is this down one, not the above one. Okay, 6.8, 2.4, 7.4. So 6.8, 2.4, 7.4, and 7.4. Then we have 8.5, 8.1, 6.1. Then we have 8.5. We have 8.1. Then we have then we had 6.1. And above we are having 3.4 and 2.0. So here goes the 3.4 and 2.0. Great. What about the before thing? So 6.6, 6.5, 9.0, 10.3. Okay, so here we are having 6.6, 6.5, 9. Then we have 10.3. Okay, after that what we are having? 11.3, 8.1, 6.3, 10.6. Okay, we are having 11.3. Then we are having 8.1. We had 6.3 and we had 11.6. Now the difference which we had talked about into the previous video as well, that difference would actually be calculated after the subtraction of both of these things. Okay, as soon as you subtract after from before, the difference would be out here. So here it is 0.2, then we have minus 4.1. Okay, let me write out minus clearly actually. It's minus 4.1. Then we are having minus 1.6, minus 1.8. Let me come down. Yes. Then we are having minus 3.2, minus 2, minus 2.9, and at last we are having minus 9.6. Okay, so these are the differences which actually I am having here. Right, so my table is now actually made out. After this, what we do? We basically take out the data for the differences. Separately, we just take that out. So I would just write here that the data for the test are the differences. Okay, so the data that we'll be taking out for the test will be the differences that we had calculated out. So that was 0.2 minus 4.1, 4.1, 1.6, 1.8, 3.22. Okay, then after that it was basically minus 1.6, minus 1.8, minus 3.2, minus 2, and we are left with two more things, minus 2.9 and 9.6. Okay, that is minus 2.9 comma minus 9.6. Yes. So these are the, now this is the data for the test, and these are the differences that will be finding out the data, and this is the data on which we'll be performing out the test. Okay, find out the sample mean. So the sample mean yes, what is the sample mean for the difference? The sample mean of the difference. What is the sample mean of the difference? So that is actually, it is represented by x bar d, and it would actually, you can calculate, and it would come as 3.13. Okay. And what about the standard deviation? So the standard deviation of the, let me now come down, the standard deviation of the differences that is basically S represented by ST, and that is 2.91. You can just verify out these values onto your own, right? So when yesterday we had discussed about, like in the last video we had discussed about the question, so that was x bar d minus mu d upon st upon under root of n. So yeah, these say all the values I had just found out for today's question, right? So this is the one which we had actually find it out. After this, what about the mu d? Let me just write out something. So let mu d be the population mean for the differences. So let that mu d be the population mean for the differences. Now what we'll be doing, we'll be using the subscript that is d for denoting out the differences. So let me write out that we use the subscript small d, that is small d, to denote the differences, right? So we will be using our subscript d, that is basically for denoting out the differences. After this, we are now having out the random variable that just put out the hypothesis test and apply out all of the things. So let's do that particular thing. I would write capital X bar d, that is equal to, I just say that random variable, let's say, and this is the, let it denote the, okay, that is not the main, that is the main. Okay, so the main difference of the sensory measurements measurements. Okay. Yes, so this is the idea for the measurement. So here we have h naught is basically mu d, and that is greater than equal to 0. Right, so basically after that, mu d basically what is that? That is the population mean of the differences. So if there is no improvement, so we can apply one more thing, that h naught is basically mu d is less than 0. Right, this is the also one thing that we can apply out, right? The score should be lower than the hypothesis, right? That we are like actually is in the question. So the score should be less than that, and the differences as well should be negative to indicate out the improvement, right? These are the conditions which actually apply out. Now we will be using out the distribution for the test, right? So what I would be doing here is that I would be just coming down and just writing out the thing here, that is the differences, no sorry, that is not the differences, that is the distribution. Okay, that is the distribution for the test. Okay, the distribution for the test. So you can just find out that distribution for the test, you can just denote that df, and you can just write at n minus 1. So that would be 8 minus 1, and which is equal to 7. So now how did I found out the 8? So just have a look over this table which was given out at this particular place. So results are randomly selected when the before matched. Okay, so basically here are total 8 points. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Right, so from there I just got to know regarding that this basically the value for n is actually 8. Right. So after this, basically now we are left with calculating out the p-value, plotting out the graph, and then finding out the sample mean and the standard deviation, comparing out the p-value alpha, and making out a decision and then conclusion. So these are some of the things which we are actually doing in the previous questions as well. So I would just give you some time to solve out these questions, this further things onto your own. Just take the help from the previous videos which you had already watched and made out the things for. So there basically you could just find out the things, and from there with the help of that you could just figure out the rest of the things which are left. Otherwise we'll be covering that into the next video. Right, so this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So in the previous video, we had discussed about the null hypothesis and the alternate hypothesis, right? We had seen that what are these two terms and basically what are the things that we have here and all those things we have discussed even with the one example as well, right? Now, basically today I'm just going to tell you one more example regarding this null and alternate hypothesis as well, and after that we're going to discuss some more things in these things. So let me quickly give you an overview that what we have discussed previously. So we had discussed about the null hypothesis that was actually denoted using H naught, right? And it was a statement about the population that will be assumed to be true unless it can be shown to be incorrect beyond a reasonable doubt, right? And then we had discussed even about the alternate hypothesis, and it was denoted by HA. So basically it is a claim about the population that is contradictory to H naught and what we conclude when we reject H naught, right? These were two things which we have discussed in the previous video. Let me move on to the same section which I had made it for today, and let me discuss one another example with you all. After that I'll proceed on with the new things, right? Okay, so my example goes here like this. So let's say my question is we want to test, okay, let's say we want to test if college students take less than 5 years to graduate, from college on the average. Okay, that is basically on the average, right? This is the thing. So now basically here what I can just say, according to the alternate hypothesis and according to the null hypothesis, I can just add here that my answer for this question is that null hypothesis, that is H naught. So basically my mu, that is my average, will be greater than equal to 5. Okay, and talking about my HA, that is my alternate hypothesis, that will be basically mu and it would be less than 5. Mu is basically my average. So this is the thing that we can just say from here, that this is the question that we want to test if college students take less than 5 years to graduate from college on the average, right? So this was the idea which we can just add on here with the things, right? Now basically let's say we had just find it out all of these things, whatever I just written. Let's say we had just find it out the alternate hypothesis and even the null hypothesis. Now what comes next? Okay, if I just write here that since the null and alternate hypothesis, I would just simply write hypo dot. So just assume it as hypothesis only, okay? Since the null and alternate hypothesis are contradictory. Contradictory means crossing with each other. Contradictory. So let's say the null and the alternate hypothesis are contradictory. Then what I can just say that you must examine evidence. You must examine the evidence to decide if you have if you have enough evidence, to reject the null hypothesis, that is null hypothesis or not. So this is the thing that you need to decide after you have just got out the null hypothesis and the alternate hypothesis values. After this is the thing that you need to decide on, that basically do you have proper evidence to decide that if you have enough evidence to reject the null hypothesis or not, right? So this evidence, actually the evidence which I'm just talking about, is it is a form of a sample data. Let me add on that thing also. So the evidence that I was talking about, so the evidence is in the form, so the evidence is in the form of sample data. Evidence is in the form of sample data, right? So after you have just found out all the things regarding the null hypothesis, you had found out regarding the alternate hypothesis, so then you need to decide that do you have enough of evidence to reject the null hypothesis or not, right? So that evidence will be in the form of sample data. Now let me just come down here. So I would just, okay, let me take our color as so as to like change a little bit here. So I would just add on that after you have determined which hypothesis the sample supports, you make a decision. You make okay, just 1 second. You make a decision, right? So basically, after you have determined that which hypothesis actually you are taking, the sample which you are having, which hypothesis it is actually like supporting. Okay, after that, if you have done this thing, so you had made a decision, right? Now basically there are two options for the decision which you have made, right? Let me just add on those things as well here. So I would just write that thing, that there are two options for a decision. Okay, there can be two options, or you can just say two conditions, or whatever you just want to say. So basically there are two options for a decision. So the very first goes like that. Okay, just let me write it as like this only, right? So it is basically they are reject, if we basically reject the H naught, okay? If the sample information reject H naught, basically it means that if the sample info which I have favors the alternate hypothesis, that is alternate hypothesis, okay? So this is the very first thing which we can have, that basically if the reject H naught, and second goes like this, hypothesis, okay, or the second one is that do not reject H naught. That is my second condition. Or fail to reject, or even just write as or fail to reject H naught. This is also even which we can just write it as another way. So second goes like that: do not reject H naught or fail to reject H naught. So this is a decision which can be made if the sample information, that is the sample info is insufficient. Okay, let me just come down here. Is insufficient to reject. Right, these are the two decisions which can okay, to reject the null hypothesis. Let me write that, the null hypothesis. So these are the two decisions which can be made here, that basically first of all that there are two options for decision. They are basically reject H naught if the sample information favors the alternate hypothesis, or do not reject H naught or fail to reject H naught if the sample information is insufficient to reject the null hypothesis, right? These are the two conditions which can be applied. These are the two statements which we can give here for the decision, right? So after you have determined which hypothesis the sample supports you make a decision. So these were the two options for the decision, right? After that, basically, even I have one table also for this hypothesis testing. Let me just make out that as well. So it is like this here. Okay, let me just come down a little bit like this right here. And now just let me quickly draw one partition type of line here. It is like this, let's say. Okay, let me shift it a little bit here. Yeah, here it will be absolutely. Okay, it's fine. Now I will just take another color. Let's say that will be red for me. Okay, so this is my actually H naught and this is actually my HA. Okay, So my first condition goes that here first sign is my equal, that is my equal sign. Now into this equal sign, if H naught is equal, then HA would be not equal, then HA would be not equal or greater than or greater than or less than. Okay, so if H naught is basically equal, then in that case HA will be not equal or greater than or less than. Right, my second condition goes like greater than or equal to. Okay, so that is great. Okay, just let me even just put out the symbol as well. It will be greater than or equal to. This is a symbol for this, right? Greater than or equal to. So if this is the condition for H naught, then HA will be less than. Okay, then in HA it would be less than like this. Okay, and my third condition goes that if H naught is less than or equal to like this, if it is less than or equal to, then in that case basically my HA would be more than. It is like this, right? So I hope that you have got a fair and a clearer idea that basically how we just do out the things here, right? Okay, just one second, and let me just include this as well. I know it will, okay, and then let me not just like remove all these things. Let me put it like this as well. Fine. So basically these are some conditions which apply onto H naught and HA. Right. So I hope that till now this point you have got a clear and a very fair idea regarding the null hypothesis and the alternate hypothesis. Even we had seen this thing also, that when you have just categorized that it is null or alternate, after that what you need to do is that, right? After that basically how to make out the decision and all those things basically you have categorized here, right? And even I have just given you some conditions regarding the H naught and HA as well, right? So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So today we're going to start out a new topic in the statistics for data science, and that I would just write that out and spell that as well, that what's the next topic that we're going to start up today. Just quickly let me take out a pen so that it is suitable for me to go ahead and write out. Yeah. So the next topic that we're going to start out here is chi-square test. Okay, this is the next topic that we're going to go ahead with in the statistics. Right. Now, when it is start out a topic, the very first question that comes into my mind is that why is the statistics necessary or compulsory to study out this particular topic, right? As well, we are having many of the topics already. We have studied a lot in the statistics. And how come these new topics and why are these particularly used? Why did these kind of topics came into existing? And all these questions I really have in my mind before starting out a new topic and before learning out a new topic, right? So first of all, I'm going to answer out all these questions, then afterwards I'll be taking you completely to the chi-square test. Okay, so let me just quickly take out a different pen color here so that I could proceed on with the writing as well, and here we go. Okay, now here I have some you could say some thinkings for you all. Okay, so let me just put on the number 1. So I will just write these things as well. Okay, so it's have you ever wondered if a lottery numbers were evenly distributed. Did you ever thought that what if the lottery numbers which are there, all of those were simply evenly distributed, then what could actually happen out? What could actually occur? Right, this is one of the wonderings which you should actually pay attention towards, right? Next, let's say and the evenly distributed numbers we were having, and if some of the numbers were occurred with a greater frequency, then in that case what would have been happened, right? Next one of the wonderings you could even go ahead with that. How about that if the types of movies people preferred were different across different age groups, right? Yes, it actually happens out that according to different age groups, the type of movies actually differs out, right? So what could happen in that? Next, basically, what if a coffee machine was dispensing approximately the same amount of coffee each time, right? So basically, all of these questions can be answered. What are the questions I just mentioned about, right? 3 to 4 questions. These can be mentioned with the help of the hypothesis testing, right? We could just simply apply out the hypothesis testing into that, and we could simply answer out these questions. Hypothesis testing we are already very much aware of, right? So I just do not need to again read that right here, right? So that was you could just answer out this questions by simply conducting out a hypothesis test. Now, basically you have to study about a new distribution here, which is completely used to determine the answers of the above questions which I had actually given you. Right here, I have just mentioned 2-3 questions. Right, that what if a coffee machine pours out like similar amount of coffee every time, and what if the type of movie differs in the type of age group, right? So in that case, now we have to study about a new distribution that would be completely used to follow out the answers, to find out the answers of these above mentioned questions, and that particular distribution is chi-square distribution, right? So I would just write that name here, distribution. Okay, here we missed out a square, so I would just add on a square, and here goes the distribution, right? This is basically what the chi-square distribution is completely used for, right? Hope I am very much clear with this particular thing. Okay, so now basically we'll be learning about many different things right here in this particular module, so I will just not waste of too much of time in this particular thing. Let me take you to the notation part of this square distribution. Okay, that basically how we denote out these all of the things, right? What's the denotation, what symbols do I use? So here goes the notation. Okay, and right here I would just take out, okay, let me go ahead with this only. Let me click on cancel. Great. Okay, so basically the notation for chi-square distribution. So basically the notation for this particular thing is, we simply write out here x, and we simply, oh, not like this, it's something like this, right? X is square, and that's approximately equal to, I would just put simply like this only, that's completely equal to x, and here goes the square, and here goes the df, right? So I would mention it like this right here. Great. So this is the notation, this is the denotation for this square distribution. This is how we denote it out actually. Okay, now what does this df actually means out here? So I would just mention that as well. So df is equal to, that is the degree of freedom, depend on how this square test is being used. Okay, this is what this df means, that it is a degrees of freedom depend on how this square test is being used out, right? So yes, this is the idea regarding this df as well, that what does it actually means out. Okay, fine. Now basically if we just want out a practical calculation using the this chi-square probabilities, then in that case we could simply use out here df is equal to n minus 1. Okay, that would actually happen. That will give you the like the probability, the calculation for the particular calculation. Okay, right, that absolutely okay. Now next, let's come down here because I have some more things to tell you regarding this denotation only. Okay, here we go. That for the x square distribution, which we had seen right above. So for the x square distribution, the population mean is mu is equal to df. So basically if you are having a distribution that's x square, so for that the population mean is mu is equal to df, okay, and the population standard deviation is sigma is equal to under root of 2 multiplied by df. Okay, I just did not put out the multiplication sign. 2 multiplied by df, right? So 2 you are already aware that what it's 2 is a simpler number. Dot is basically multiplication. What's that df? That's df is the degree of freedom which we had seen right above, right? So whenever you are having the x square distribution, so in that case, for finding out the population mean, the formula is mu is equal to df, and for the population standard deviation, it is sigma is equal to under root of 2 point df, right? Next, the random variable is shown as it's not that x, like it's completely like this, okay? That random variable is shown like this, shown as this much, and but it could be a but maybe any, let me just calm down first of all, but maybe any uppercase. That's not related to right here, because maybe some of you must be having out the doubt that the denotion for this random variable and it is absolutely same. So how would I differ that? What is it and what is that actually? Okay. So in that case, this is a sentence which I have written. You could follow this out. Okay. Now we have the random variable as well. So the random variable for the random variable for the chi-square distribution, the random variable for the chi-square distribution which has the degrees, that is k. Okay, I would write out with k degrees of freedom, is the sum, let me just calm down, is the sum, okay, 1 second, right here. So is the sum of k independent squared, is the sum of k independent squared standard normal variables. Right? So what's the denotion for that? So the denotion for that is x square is equal to, here we have z1 square plus, then we have here z2 square plus, and here we have zk square. Okay. So yeah, this is the denotion regarding the degrees of freedom as well for this particular sum. Now, right, we're letting you know about the 2 facts about the chi-square distribution. We have 2 facts here regarding this particular thing, okay? So I just give a little bit time regarding that as well. So let me quickly take out a pen right here once again, a different color. Okay. So here it goes, that facts about the chi-square distribution. Okay, this is the facts about the chi-square distribution. Let's come down here, go ahead with the very first one, and the very first fact is that the curve which we have here is non-symmetrical, and is skewed, sk is skewed to the right. So the curve which we are having here in the chi-square distribution, that's the non-symmetrical, and it is skewed towards the right. Okay. Next, that there is a different square curve. There is a different square curve for each DF, for whatever the each DF, like for whatever the degree of freedoms differently you are having. So for every of them, we have a different set of curve. We have a different curve which we get out by the relevant values and the points we get out, right? So yeah, hope I am very much clear with you all, with all of these things regarding to you, regarding the chi-square test, that what it is, what's the notation for that, and basically what's the fact regarding this particular thing, right? We'll be seeing about more things in the next videos. So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So into the previous video, we had seen regarding the chi-square test, that what it actually is, right? We had seen a clear definition regarding this. Even we had studied about the notation, and then we had read about some facts regarding this particular distribution, right? Now what I'll be doing is that, or what I'll be taking you here is, first of all, I'll be giving you an overview regarding this particular two facts that we have studied. I would show you these things in a form of, we could say, in the graphs, and next I'll be taking you towards some more facts regarding this particular distribution, right? Hope I am very much clear with this particular thing. So let me just quickly get out some space for making out this plots. Now what we are having here is that the two facts which we have studied is, the very first one was that the curve is non-symmetrical and skewed to the right. Basically, we had seen that the curve which we get in this particular distribution, the very first thing is that it's completely non-symmetrical, right? Secondly goes that it's basically skewed towards the right. Skewed towards the right means that more portion of the curve comes onto the right hand side. Next, we had seen that there is a different chi-square curve for each DF. So as soon as the DF values, that is the degree of freedom values, change out, till that same case as well, the distribution, the graph as well changes. Right, so the time where you are changing out the degrees of freedom value, the graph will as well change out. Let me show you these two demonstrations with the help of a curve. Then I would move forward with rest of the graph. So here I just made out one single like this, and I'll be making out one more x and y square like this, right? This is how I'll be putting up the things. Next, what I'm going to do is that I would simply take out one of the colors, and with the help of that particular, I'll be showing you the graph. See, let's say here I'm taking the value for DF as 2. Okay, the value for DF I'm setting as 2 for this very first graph, this particular graph which we are actually having out here. Okay, now into this particular, what I'm going to do is that I'm simply going to make out this graph regarding which is having the degrees of freedom as 2. So the graph would somewhat look like this, but the downside of this would not be. Let me just go right here. Yeah, this is how this particular graph is going to look out. Okay, this is how it will completely look. So this is the case where we are having the degrees of freedom value as 2. Right, I just made it onto that particular place where the degrees of freedom value is completely 2. Now, what if I change out the value for DF as 24? If I just change out the value for DF as 24, so into that case, it would somewhat go ahead like this. This particular curve will be appearing, then it would be coming, okay, not like this, 1 second. Not from here, right here. Let me just take out the pen once again. Where has it gone? One second just, okay. Right here, click on OK. I'll be going out from here, exceeding this particular point, coming down from here, and the turn is not that much sharp. It's something like this, okay. Doing like this and going ahead with this particular thing, right. Now, as soon as I changed out the value for the DF, the particular plot as well changed of mine, right. This is what when DF value was 2. And this is the plot which has came when the value for DF is actually 24. Right, so hope you are understanding the difference between both of those graphs, the symmetry of these graphs, and basically how are these particularly made out. Right, hope I am very much clear with this particular thing. Now what I'll be doing is that I'll be taking you downside again, and now let's study about the rest of the facts regarding this particular interval. So now let me take you to the next points which we have out here for this particular graph. Okay, so here goes the number 3 part. So it is that the test statistics for any test is always greater than or equal to 0. Okay, this is the case that the test statistics for any test is always greater than or equal to 0. One another point for the chi-square distribution. Moving towards the point number 4. So here the next point we are having that when the value for DF, okay, when the DF value is greater than 90, okay. So in that case the chi-square curve approximately, I would just write simply approximate, okay, when the value for DF, that is degrees of freedom, wherever that is greater than 90. So the chi-square curve approximately the normal, right? Like whenever this particular condition is there, so it means that the distribution curve which is going to made out, that is approximately to the normal curve, right? Now for the value for x approximately equal to this was like this x square, and here goes up till 1000. So the mean which we are having, so the mean, that is the mu, the value for mu, okay, that is equal to df, and the value for df is equal to 1000. So here the condition goes like that for the x like the capital X which we are having out here, that's approximately equal to this particular x, and that's approximately equal to x square, and the value for that is around 1000. It means that the mean, right, the value for mu and the value for df both are absolutely same, and that is 1000. Okay, now next, what about the standard deviation regarding this particular? And I would just write out, and the standard deviation, that's SD, right? And the standard deviation, that sigma, is equal to under root of 2.000, like this. Okay, and that would be, if I just do out the root for this particular, so it's gonna come up to somewhat like 44.7, somewhat like this. Okay, so therefore what I could just conclude and write out from here, so I would just write therefore the value for capital X is approximately equal to n, that's the normal, and here goes the 1000 comma, and here put on 44.7, right, and that's completely approximately, it's not that very absolute, so I will just simply put on APP, that's, it means that it's approximately out that value, not too much okay, or not too much like that, right? Next, we are having the point number 5, that the mean mu is basically the symbol which we denote for putting out the mean, right? So the mean mu is located just to the mean mu is located just to the right of the peak. So whatever the peak, and whenever we just at whatever the place we just get out the peak for this particular value of df. So at the right hand side, okay, just remember that on the right hand side of the peak we have the value for the mean, and that is completely mu, right? What I would just do is that let me just come down here for a while, and let me quickly plot out the graph regarding that as well. So here we go with this particular okay, not like this, it's not the one which I needed actually. Okay, this one works actually fine. And how I'm going to plot it out, so it's like this, then it goes like this, it goes like this, and it goes out like this, right? And here we have the mu. So wherever I just find out the peak of this particular curve, onto the right hand side we have the value for the mean, and that's mu, right? So hope I just made out these things very much clear regarding this particular graph. The first one regarding the graphs and what are the different facts which we have here for this particular distribution that we have to keep in mind. Hope I am very much clear with all of these things at this particular place, right? So I'll be meeting you in the next video with some more new topics regarding this similar distribution. So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So, behind the previous video, we had studied about the different topics, different facts regarding this chi-square distribution, right? Now, I am going to go ahead with the topic, and let me quickly take out a pen first of all, then I will let you know topics, right? So, the topic name that I'm going to go ahead now with is goodness of fit test. Goodness of fit. Okay, let me just quickly put on the text similar to this only right here. Okay, so this is the topic that we are going to go ahead with. That's the goodness of fit test. Okay, so I'll be letting you know regarding this particular. Okay, so basically what happens in this, I would just start writing out here as well, that in this type, one second, let me close this right here at this particular place right here. Okay. So it goes that in this type of hypothesis, test, what do you do actually? Okay, in this type of hypothesis test, you determine out that whether the data, okay, that's known as the fit, which I was just referring above to. So here in this particular distribution, we have some different names as well. So what it goes that here, whenever I just use out the word that's fit, so it means about the data, right? Whether the data that is known as the fit as well. A particular distribution fit a particular, okay, that's particular, right? CULAR, right? So in this type of hypothesis test, you determine whether the data fit a particular distribution, or not, right? So here goes the not. Fine. So it basically, in this type of hypothesis test, you determine that whether the data means the fit as well, a particular distribution or not. Basically, it is a particular distribution or not. This is what you determine here. Okay. Now, basically, next what you do that, let's say I just take out an example, right? That you may suspect your unknown data to fit out a binomial distribution. Right, for example, I just take out an example that let's say you may suspect your unknown data, okay, to fit a binomial distribution. So in that case, you could use out a chi-square test, okay, chi-square test, right? So that's meaning that the distribution for the hypothesis test is that chi-square, okay. Now, so what is this completely used for? So it is completely used for determine that whether there is a fit or not. Means whether there is a fit or not into this particular test. It is completely used for defining that thing out, right? Next we have some important points to keep in mind here. So I will just go down and let you know that particular thing right here. So here it goes. The null and the alternate hypothesis for this test may be written in sentences. So null and the alternate hypo for this test may be written in sentences. Or basically next condition is that or may not or may be or that's or may be stated as equations, or maybe stated as equations or inequalities, maybe stated as equations or equalities, right? So the null and the alternate hypothesis for this test may be written in sentences or may be stated as equations or inequalities, right? So the test, how we just do that out, so how we just like perform out the test right here. So it goes that the test statistic, it's like this right here. So the test statistics for a goodness of fit test is, what's the formula which we have out here? Just let me get out some space for writing, because that's one of the important formulas which we are having right here. So here it goes for the sigma, and downside it goes from k, okay, sigma k. Now here we have big O, that's like capital O minus E, okay. Let me write out the E clearly, because right here E. Putting like the bracket coming down, and here again we have the capital E, and that's the square, right? This is a formula which we completely use for the test statistics for a goodness of fit test. Now, what are these particular things which we are having here? What are these meanings and what are they referring to? So capital O refers to the observed values. And we just see that as a data, right? Big O refers to that. Next we are having the capital E. What is that capital E? So it's the expected values, okay, it's the expected values which we get from the theory of the data, from theory which we get that out, okay. Next we were having the value for k was also mentioned up downside right here. So that was the number. So it's the number of different data cells. It's the number of different data cells or categories, we could as well say, or categories. So here goes the categories, right? So let me just calm down for a short while here. Great. 1 second, let me go a little above. Fine. So the value for O is called as the observed values, that's from the data. The value for capital E is the expected values, that's from the theory. And the value for the small k is the number of different data sets or the categories which we have, right? So yeah, these are some of the you could say some of the more specifications, some of the meanings regarding the different symbols which we have for the test statistics for a goodness of fit test, right? Hope I am very much clear with this particular thing as well, right? Now, next what I'm having, let me just now come down a little bit and explore a little bit more things regarding the same thing. Okay, excuse me. So yeah, here goes that the observed OBSG, yeah, right here, fine. So the observed values are the data values. Observed values are the data values, and the expected, okay, here goes the expected. So the observed values are the data values, and the expected values are the values you would expect, are the values which you would expect to get if the null hypothesis were true. Right, so the observed values are the data values and the expected values are the values which you would expect to get if the null hypothesis were true. Right, so there are n terms of the form, so it could be, I would just write that as well. So it goes that there are n terms of there are n terms of the form. And what's the form which is having n terms? That's o minus e whole square. Let me just go down a little bit more. Right, so o minus e whole square and divided by e right here. Right, so this particular form is as well having n terms. So in that case, this is one or more. That's o minus e, the whole square divided by e. Right, so let me now just go above right here and 1 second. Okay, so today we studied about the goodness of fit test, that what it actually is, what we meant by fit. What's the formula that we use for finding out the goodness of a fit, right? So we have the formula that sigma k. In the bracket we have o minus e whole square divided by e. What's the e? What's the o that we are having? So that's the observed value. What is E that we are having? That's the expected value. What's the value for K? So that's the number of different data sets or categories, right? And then we had seen about that there are n terms to form this particular formula that we have studied, O minus E whole square divided by E. Right, hope I am very much clear with this particular thing, that how you could go ahead with this particular topic and what it is. Now we're moving forward with some more things in the new video. So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So in the previous video, we had studied about the goodness of fit test, right? So we had studied that in this particular type of hypothesis test, what you do, you determine that whether the data, or which you call as fit, is a particular distribution or not, right? This is what you do. Now, the null and the alternate hypothesis for this test may be written in sentences or may be stated as equations or the inequalities, right? The test statistics for a goodness of fit test which we have here is sigma k, and after that we have in the bracket o minus e to the whole square divided by e. What's the value for o that we are having? What is that actually? How to find it out? So value for o is actually the observed value of the data, right? What's the value for e? So the value for e is the expected value which is from the theory. And what's the value for k which we are having? So that's the number of different data sets or the categories. So the observed values are the data values and the expected values are the values which you would expect to get if the null hypothesis were true. So basically there are n terms of the form, that is o minus e to the whole square divided by e. Now we have some more things in this particular interval as well, so I will just begin with that. So the degrees of freedom, G D E G R double E S, okay, the degrees of freedom are, what's the value for the degrees of freedom? So that is df is equal to number, okay, I will just simply write number of categories subtracted by 1. So this is what the value for df is. It's the number of categories minus 1. Right, so hope I am clear with this particular thing first of all to you. Next, what I'm having, next I am having that the goodness which we have for the fit, right? So the goodness of fit test is almost always right-tailed, The goodness of fit test which we have is almost right-tailed. As I have already mentioned out this thing previously as well, that what are the goodness of fit test we are having, that's almost always onto the right hand side only. That's always right-tailed, right? Next we have that if the observed values and the, let me just go down right here. So if the observed values and the corresponding the observed values and the corresponding expected values are not close. Expected values are not close. Now, if basically the observed values which we have founded and the corresponding expected values, if both of them are not close to each other, then basically what we say, then the test statistic, here goes the statistic. If the observed values and the corresponding expected values are not close to each other, then what we say? We say then the test statistic, okay, then the test statistics can get very large, and will be way out in the right tail of the let me just come down right here. So we can see that if the observed values and the corresponding expected values are not close to each other, then the test statistic can get very large and will be way out in the right tail of the test which we are talking about, and that's the chi-square curve. And here goes that particular curve. Right, so basically what we studied right here, what we meant from this, one second, let me take on the cursor onto hand, right here it goes. So we had seen that the goodness of fit test is almost always right-tailed. Right, if the observed values and the corresponding expected values are not close to each other, then basically what happens, then the test statistics can get very large and will be way out in the right tail of the chi-square curve, right? This is what actually happens. Now here I have a note to be written out. I will just go on like this note, and that is that the expected value, the note is that the expected value for each cells, let me just come down. It goes, okay, one second, let me remove out this number which are written, fine. The expected value for each cell needs to be at least 5 in order to use the test, right? So here we have out a note that the expected value for each cells need to be at least 5 in order to use out that test. So let's say I just want to use out that particular test. So in that case, it shall be like the expected value for each cell which we are having, that shall be at least 5. Okay, this is the one of the condition which applies out, that it shall be 5. Then only we will be able to use out that test. Wait, I'll be giving you now a quick revision for what are the things we have studied from the starting in this particular distribution. So we had studied about, first of all, the notation, that puts a notation for the chi-square distribution, that's x square approximately 2x square df. Right, what's that df? df value is equal to n minus 1. What is that df known as? So it's the degree of freedom which depends on how chi-square is being used. Then we have that for x square distribution, the population mean is mu, that's equal to df, right? And the population standard deviation is sigma, that's equal to under root of 2 point, that's 2 multiplication df. The random variable which we have, the random variable is shown as x square but may be an uppercase. The random variable for the chi-square distribution with k degrees of freedom is the sum of k independent squared standard normal variables, right? This is how we just use, and this is how we denote x squared is equal to z1 square plus z2 square plus up till zk squared, okay? Now, what we have the facts regarding the chi-square distribution, so that is that the curve is non-symmetrical and is skewed towards the right. Next, there is a different chi-square curve for each of the TF. So as I had shown you in the graphs as well, that when I have taken the degree of freedom as 2, so the graph is different. When I have taken the value for GF is equal to 24, so in that case as well the graph is different. So it proves that out, that as soon as the values or the degrees of freedom differs, that your graph will as well differ out in those cases. Okay, the test statistics for any test is always greater than or equal to 0. So test statistic which we have for any test is always greater than or equal to 0. When the value for DF is greater than 90, so in that case the chi-square curve approximates the normal for like we have x belongs to x square 1000. So in that case the mean is mu is equal to DF is equal to 1000. Standard deviation is equal to sigma is equal to under root of 2.1000, and that's equal to, it's not point, that's actually multiplication. Okay, make sure to remember that out. Above we have studied out the formula as well. Where is that? Right here we had seen sigma is equal to under root of 2 multiplication df. Right, in the same way right downside as well we are having the same thing. Now therefore the value for x we have approximately equal to n, and that's 1000,44.7. Okay, and that is approximately. The mean, that's mu, which is located just to the right of the peak. As I told you that the mean which we have here is whatever the peak we are having for that particular graph, it's just located to the right hand side of that particular peak. Right, now what's the goodness of fit test? So in this particular type of hypothesis test, what you do, you determine that whether the data, that's the fit, we call it as data or a fit, is a particular distribution or not. Right, this is what we define out here. Then we are having that the null and the alternate hypothesis for the test may be written in the sentences or may be stated as equations or inequalities. Right, so the test statistics for a goodness of fit test, the formula which we have seen was sigma k. We have O minus E whole to the square divided by E. What's the value for O? So that's the observed values, that means the data. What's the E? E is basically the expected values, that is from the theory. What's the K? So K is the number of different data sets or different categories, right? So the observed values are the data values and the expected values which you would expect to get if a null hypothesis were true. So expected values are the values which you would expect to get if the null hypothesis was true. There are total n terms of the form, that's of this particular form, that is O minus E whole to the square divided by E. What's the degrees of freedom that we are having? So that is DF is equal to number of categories minus 1. The goodness of fit test is almost always right-tailed, right? It is observed values and the corresponding expected values is not close to each other, then the test statistic can get very large and will be way out in the right side tail of the square curve. Note that the expected value for each cell needs to be at least 5 in order to use out that test. Right, hope I am very much clear with this particular thing regarding the quick summary whichever I have mentioned up here regarding all the things. Right, we'll be discussing about some more topics in the further video. So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So now we're going to study and we're going to learn about the test of independence, a new topic which has been added into this particular chi-square distribution. Okay, so what I'm going to do is that let me quickly take out a color from here and okay, let me choose out a color from this particular place. This time let's take out this one. Okay, right here. So name for my topic is test of, and here goes the independence. Okay, test of independence. Okay, right here. Now we'll be learning about this. We'll be seeing what it is, what's the formula and all the things, right? So I will just let me come down for a while, get out some space, right? Here, let's start writing out the things here. Okay, so here it goes that the test of independence involves using a contingency table. That's right. That's right. That's right. Okay. So test of independence involves using a contingency table, right, of observed in the bracket we have of observed data, and here goes the values. Right. So yeah, this is the test of independence. That the test of independence involve using a contingency table of observed data, and that is the values which we have. Right. Now next we have that you first saw a contingency table, contingency table. Okay, this we have like studied a little bit, not that much in detail when we have studied about the previous topic. So there we have studied about this particular table a little bit, not that too much. Okay, so yeah, we had seen about this. So what's here that we are having the test statistic, test the test statistic for a test of independence, So test statistic for a test of independence is similar to that of a goodness of fit test. Right, this is what here is the task. Basically, the test statistic for a test of independence is similar to that of a goodness of fit test. Right, now what's the formula that we are having here and that we actually follow out? So I just put on the sigma here, sigma it lies, and downside I'll be having I dot, and here goes the j. Okay, I dot j we are having onto the downside. Okay, next after that, here above again we are having O minus E whole square divided by E. Again we are having out the same thing only. Right, now what are these relevant notations which I had put on? So where O is equal to, what's the value for the O? So O is basically the observed values. Okay, O is basically the observed values. What about E? So E is basically the expected values. Okay, what's the small I? So the small I is the number, so it's the number of rows in the table. Okay, so what is I? I is the number of rows in that table. And what about J? What are we having here? J. So J is the number of columns in the table. Right. So basically here O is the observed values, E is the expected values. What's the value for I? So I is particularly referred to as the number of rows in that table. What are the number of rows we are having in the table? That's completely refers to the I. What about the J? So J refers to the number of columns in that table. So what are the number of columns we are having in the table? It refers to that. Right, now let me quickly come down, and I have some other points to add onto this particular place as well. So there are I dot j terms of the form that is O minus E whole square divided by E. So basically in the previous one as well, we had studied about the good fit. So there we had seen that there were n terms for this particular form. Right, now when we are into this particular topic, here we are seeing that there are I multiplied j terms of this particular form, that's O minus E whole square divided by E. Right, now let's come down here, and right here now I have some other points to add at this particular place as well. So basically a test of independence INDE, yeah, it goes like this. Okay, so a test of independence determines whether two factors are independent or not, right? So basically a test of independence defines that whether two factors are independent or not, right? This is uh, what kind of result we get from a test of independence, right? Okay, it completely defines how that it even determines that whether these two factors which we are having that are independent or not, right? Next we are having some more terms, some things here to notice out as well. So I will just write that you first encountered the term independence DENCS. Right, so for this particular independence term, we had already studied this thing as well before. We had deal with this particular things we had seen regarding the independence in some of our previous starting videos, but I would just not go into that. When we will be taking out some examples, then I would go. Okay. So basically a test of independence determines that whether two factors are independent or not. Okay. So it basically determines out that whether the two factors are independent or not. It basically lets us know that the two factors which you have taken that are independent or not. Now I have a note to put up here onto this particular place. Let me put on some note as well here. So the note goes that the expected value for each cell needs to be at least 5 in order to use that okay, not to use that, you use order to use this test, right? Now what it is said here, it is said that the expected value that we had already find out, that was denoted by the alphabet, that's E, right? So the expected value for each cell needs to be at least 5 in order to use out this particular test. So we should have at least 5 value in order to use out this particular test that we are studying. So you could say that it is one of the like a range, or you could say it's one of the minimum value that needs to be satisfied for using out this particular test that we're studying. Let me go above and give you let me just quickly first of all take on the cursor, then I would let you know regarding some things right here again. So here we are having that the test of independence. So yeah, we have this condition that for this particular test of independence, we shall have the value, we should have a value which is 5. Okay, then only we will be able to use out this particular test of independence test. So you could say it's a like range or anything, I can mention that out, right? So hope you got out this idea as well regarding this particular thing. The formula which we go ahead is sigma I dot j. In the bracket we have O minus E whole square divided by E. Right, so hope I am very much clear with this. Next topic, the new topic as well, which is test of independence. And now we'll be seeing up some new topics in the further videos. So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So now we'll be studying about the chi-square distribution test for the homogeneity. So let me quickly take out a color here. Let's say I just took out this particular. Let me put on the heading as well so that we could just go ahead. Right, so my heading for today is the chi-square. So here goes the square distribution. So here it is distribution test for here, okay, one second, test, and here goes for homogeneity. Homogeneity, right? This is the topic that we are now gonna study. So I would take out a new color here so as to begin here and write out the relevant things, right? So let me just come down at this particular place and let me start on the writing here. One second, right here. Okay, fine. So we had studied about the goodness of fit, right? So what does that is used for? Let me write that as well. So we had studied that the goodness of fit test, the goodness of fit test can be used to decide. It can be used to decide out that whether a population. I will just simply write pop and put out a dot. So the goodness of fit test can be used to decide that whether a population fits a given distribution. Here goes the fits a given distribution, comma, but the goodness of fit test, but the goodness of, let me just go down here for a file and yeah, so but the goodness of fit test, here write out that test, but the goodness of fit test will be basically not be able to compare that whether both of those populations follow same unknown distribution, right? It will basically not be able to follow up that whether both of the fit tests which we are having, both of the populations follow out the unknown distribution or not. So in that case, we have a test that is called the homogeneity, test of homogeneity. So I would just write that a test. I would just write out a different test actually. Okay, a different test, and it is called a different test, and it is called the test of homogeneity. Test of homogeneity. Okay, so we are having out a different test, and that particular test is called as the test of homogeneity. Fine. Now, what that can be used for? So that could be used for making out a conclusion about whether the two populations have out the same distribution or not. So this particular test of homogeneity, what it basically focuses on, what it basically lets us know. So it lets us know that whether the test which is called as the test of homogeneity, whether it can be used to make out a conclusion about the two populations, whether they have out the same distribution or not, right? So basically, to calculate out the test statistics for a test of homogeneity, what we do, we follow out the same procedure as we had done it for the test of independence, right? As we find out the test of independence, in the same procedure we follow out the test of homogeneity as well, right? Okay, now let me come down, and here we have something to let you know regarding this particular. So let me just note down all of those things. First of all, I have a note mentioned up here. So the expected value for each cell needs to be at least 50, sorry, not 15, it needs to be, I would just mention that out here, it needs to be at least 5 in order, to use this test. Now, this is the condition that satisfies out here, that the expected value for each cell needs to be at least 5 in order to use out this particular test. Now, we have some notations here in this particular test of homogeneity as well. So, let me introduce you to all of those as well. So, first one we are having here for the hypothesis like this, right? So, what is this hypothesis actually? The denotation is H0. Okay. Now, next we are having that the distributions of the distributions of the two populations right? So H0, that is H0 is a symbol. So what is that referring to? It is basically referring to the distribution of the two populations are the same. So here goes are the same. This is what it refers to, okay? That the distribution of the two populations are the same. This is about H0. Now, next we are having HA as well. If you have studied out my previous lectures as well very carefully, so you remember out that we already discussed about H0 and HA once in one of the topics, null hypothesis and alternate hypothesis, right? Yes. So HA here it goes that the distributions. So it is basically the distributions of the two. Let me just come down. So HA is the distributions of the two populations are not the same. So HA that means that the distributions of the both of the populations of the two populations are not the same. Now, for this particular, what we have the test statistic. What we have here for the test statistics for this particular test of homogeneity topic, right? What we have out. So test statistics is that you could use out a x squared test statistic. You use a x squared test statistic. Full stop. Basically what it is computed. How do we just calculate out? Let me just write that downside, okay? So it is computed in the same way, as the, so how is this particular test statistics computed? So it is computed in the same way as we just calculate out as the test of independence. So as we used to calculate out the test of independence, in the same way we just calculate out the test of homogeneity as well, right? What's the degrees of freedom? That DF value which we are having here. So that's again the same number of columns minus 1. It's again the same which we were having previously, number of number of columns minus 1. What are the requirements? The requirements are basically nothing more. So basically it's that all the values in the table shall be greater than or equal to 5. It should basically not be less than 5. So I would just write that out here as well once. So requirement. So yes, the requirement which we are having out here is that all the values in the table must be greater than or basically, or what are the values we are having in the table that must be greater than or it must be equal to 5. So let's say we are having out any of the value. Let's say I just simply take out the value. I just put on a denotation. Let's say that is A. Okay. So requirement is that this particular A shall be greater than or equal to 5. This particular condition is important to get satisfied. Okay. If this is not getting satisfied, so in that case you simply could not apply out this principle, this test of homogeneity, right? Hope I am very much clear. Now, what are the common uses which we have out here for this particular? So I will discuss that as well. So let me put on the heading. Let me first of all go ahead and get out some space for me. Great. So here we have the common uses. So what are the common uses as well that we could apply? So common uses are that for comparing. So what are the conditions where you could use that out? So it's for the comparing the two populations. So for comparing out the two populations, let's say example is that men versus women, right? Greater versus smaller, after versus before, east versus west. So these are some, or let's say I'll just put on one of the cases as well, east versus west. So yeah, these are some of the common uses which we have here and that are used for comparing the two population. So this is the case where this particular is used out, this particular test is used. Now one another is that the variable which we are having, the variable is categorical. The variable is categorical with more than, with more than two possible response values, with more than two possible response. And just let me quickly go down. So variable is categorical with more than two response values. So these are some of the conditions which needs to be satisfied and which are compulsory to get satisfied for using out this particular principle, this particular test that we are having right here. Right, so hope I am very much clear with these tests which I have introduced you to regarding the chi-square distribution and the test for homogeneity. So basically we'll be seeing about more things in the next video. So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So now today we are going to discuss about the chi-square distribution, and we are going to say about the comparison summary of the chi-square test, goodness of fit, and the independence and the homogeneity. So till now, what are the topics we have studied in this particular distribution? We are going to take out a summary of all these and put out some comparison factors between all the topics which we have studied till now in this particular distribution. Right, so hope I'm very clear with the idea that what we are going to follow. So let's get started up here, and what I'm going to do is that I'll be simply taking out a color so that I would just start writing out in a short while. Okay, here we go. So I will just put on simple heading, that's the comparison. Right, yeah, it actually works out. Fine. So I'll be comparing regarding the chi-square test, and in that I'll be going for the goodness of fit, I'll be going for the independence, and even I'll be going for the homogeneity. Fine. Okay, let's get started up here. So you have seen, so I will just start writing out the things as well. So it goes like, you have seen the, what was the denotion that we used? That was like this, right? This was the denotion that we used. That this test is statistic. I will just write out here statistic, right, like this. Great. So you have seen that the x square, that's the test statistic, is used in three different circumstances, right? So basically now I'll be doing out the comparison regarding all of these, and we'll be like discussing about a quick summary regarding all the three. That was goodness of fit, we were having independence, and next we were having the homogeneity, right? So for writing and comparing all of these things, let me just take out a new color so that the things differentiate a little bit between each other, right? So yeah, it's okay, and let me even get out some space as well. So yeah, here we go. So I'm having here the goodness of, and then we are having here as goodness of fit, right? Now basically what we need to decide here with the goodness of fit, that fit, and what we actually do from here. So the complete use of goodness of fit is basically it helps us to decide that whether a population with an unknown distribution fits a known distribution or not, right? This is what this particular factor lets us know, that basically we need to use out the goodness of fit test to decide that whether a population with unknown distribution, that's called as a fit, is a known distribution or not, right? So in this goodness of fit, we have just simply the case that we simply have a single qualitative survey question, right? Or basically we have an experiment that has some single outcome from a single population. So under the goodness of fitness, whatever the things work and whatever the things which we are having, so that depends on the outcome of the experiment, right? Okay, that's okay. Next, basically what it is typically used for, so it's typically used to see out the population, right? It basically used to see out the population, that if the population is uniform or the population is normal, or basically if the population, one of the population is same as the other population as well, right? So this is what, and this is where this goodness of fit actually works, and this is where this goodness of fit basically is used, right? I would just quickly write out a quick summary thing regarding this particular. So I could write it out in such a way that used to see that if the population is uniform, or the population is normal. So yeah, this is the main thing where it is used, that it's basically used to see that if a population is uniform or basically the population is normal, right? Now, hope I'm very much clear with this particular thing. And basically here onto this goodness of it, we are having null and the alternate hypothesis. So already we have discussed a lot in previous topics as well, and right here in this particular as well, I just told you regarding the null hypothesis and the alternate hypothesis. So null hypothesis was basically denoted by H naught, right? And it basically what it is, it's the population fits the given distribution. So whatever the distribution we were given, it basically fits onto that particular, right? Next I was having HA, that was my alternate hypothesis. So into that case, the population does not fit out the given distribution. So this was a short difference between the null hypothesis and even between the alternate hypothesis, right? Next we are having the next factor, that is independence. So I would just put on a quick topic over here, that's the independence. So here goes the independence right here. Okay, yeah. So we have the independence. Now basically what it is completely used out for. So whenever we go with the test for independence, so basically we decide whether the two variables are independent or they are dependent, right? Whenever we just use out this independence factor, whenever we just go with the test for the independence, so we just perform out this particular test so as to check out, so as to assure that whether the two variables which are given to us, you could say variables or factors, that are independent or that are dependent. It depends, right? Now, in this particular case, there we have the two qualitative surveys. In the goodness of it, we were simply having one qualitative survey, right? Okay. Now, here into the independence factor, we have two qualitative survey questions, or you could say as experiments, okay? So, basically, what's the main goal when you are using out this particular test? The main goal is that it basically, we need to see it that if the two variables are independent or related, that is dependent. So if the two variables are unrelated or related, this is the main goal for carrying out this particular independence test, right? Here as well we are having out the null and hypothesis test. So that is H naught and HA. So H naught is the basically that the two variables are independent, and HA is the two variables are dependent. This is regarding the H naught and the HA, right? Fine. Let me just get out some space. So let me just go down. Write out here the next very third one, and that's we are having the principle of homogeneity. Right. Now we'll be talking about a quick summary regarding the homogeneity principle that we have studied out. So what is that? What was that used for? So basically this is one of the tests which is for the homogeneity. It basically helps us to decide that if the two populations with unknown distribution have the same distribution as each other. Let's say there are two populations that are having unknown distribution, right? So it is basically used to check that out, that whether two populations which have unknown distribution have the same distribution with each other or not, right? This is what the homogeneity test actually does, and this is the place where this homogeneity test actually works upon, right? And in this case as well, we will be having one single qualitative survey question, right? Or you could say experiment, fine. Again, there are two types of hypothesis. You have the null hypothesis, you have the alternate hypothesis. So for null, basically we have the two populations follow the same distribution, and for alternate hypothesis, we have the two populations have different distributions. So in the null one, we were having the same, and in the alternate, we were having the different, right? So yeah, this was about the all the three of the summary regarding all the three. That was goodness of fit, independence, and the homogeneity. So in the goodness of it, we were simply having one single that particular thing, and into that we were having two hypotheses, null and alternative. So null hypothesis was used basically the population fits the given distribution, and alternative was basically the population does not fits the given distribution, right? Then we were having the independence. So in independence, what was happening? In that as well, the null hypothesis, in that we were having two variables which were independent. Variables are as well called as factors. You could call them as factors as well, okay? So the two variables or factors are independent in the null hypothesis, and when I talk about the alternate hypothesis, so in that case the two variables, or you could say as factors, are the dependent. Right. Next, I was even having about the homogeneity. Regarding the homogeneity, that's what it is. So here in the homogeneity as well, we are having the null and the hypothesis. So null hypothesis here in this particular case was that the two populations follow the same distribution, and about the alternate hypothesis was that the two populations have different distributions. Right, so hope I made the quick summary regarding these things very much clear to you regarding that what's that goodness of fit and what are the null and alternate hypotheses there. What about the independence and what are null and alternate hypotheses, and what about the homogeneity? So in that case again, what are the null and the alternate hypotheses? Right, hope I am very much clear with this particular thing. So we'll meet you with some new topics in the next video. So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So now we are going to discuss about the test of a single variance, right? So now the topic that we are going to follow, and that is the test of single variance. So what I would do is that I would get out some space here. I would just take out a different color so as to write out the things. And okay, where is that? Yeah, right here. Let me put on the topic first of all. So the topic which you're going to follow is test of a single variance. So here goes the single and here goes the variance, right? So yeah, this is the topic that we are going to follow, that is test of a single variance. So let's see that what here we have in this particular one. So I would start writing up, and with the writing only I will explain you the rest of the things, right? So here goes that a test of single variance assumes that the underlying distribution is normal, right? So the basically what this particular test of single variance is used for. So the test of single variance assumes that the underlying distribution, the distribution which we are having, that's completely of the normal form. Okay. Next we have the null and alternate hypotheses. The null and alternate hypotheses are stated in terms of the population variance, or basically, or you could say, or that as well means the regarding the population standard deviation, right? So the null and the hypothesis, the null and the alternate hypothesis, which we have right here for all of the ones. So the null and the alternate hypothesis are stated in terms of the population variance. So whatever the null and hypothesis we get here and whatever we just like find out and all the things. So those are stated in the terms of the population variance, or you could call as population standard deviation as well, right? So finding out the hypothesis onto this case for the test of single variance, that is in the you could say population variance form, or you could say in the population standard deviation form. Right now, what are the tests that we are having? What's the formula which we have out here? So let me just go above. Right here. Okay. Now let me put on the formula. So the test statistic is, what's the test statistic that we are having out here? So that is n minus 1 multiplication s square divided by sigma square. So this is a test statistic which we are having out here. It's n minus 1 multiplication s square divided by sigma square, right? This is the formula which we have out here. Now what are these terms referring to? Whatever I had just mentioned up here, so let's see that out here. So in the one which I mentioned at the very starting, that is basically the total. It's the total number of data, right? So the term which we are using out here, which is n, that is the total number of data, right? Now coming to the new line, here I have the s square. So what is that s square? So it's the sample variance. So it's the sample variance, right? And next I'm having the third one, that's the sigma square. So that sigma square is the population, it's the population variance, like this, right? So for n we are having the total number of data, for s square we are having the sample variance, and for sigma square we are having out the population variance, right? So these are the different denotions which we are having for the terms which we have used above in the formula. Okay, now next thing is that basically we have one more thing here to be discussed out, that now you may think think of S as the random variable in this test, right? You may think of S as a random variable in this test. So degrees of freedom, I would just come down and then write it out. So okay, here it goes, the degrees of freedom. So the degrees of freedom which we are having, right, the degrees of freedom are, and that is df is equal to n minus 1. So the degrees of freedom we are having is n minus 1, which is similar to all of the ones which we have as well studied before as well. Okay, it's completely similar to those, right? So df is equal to n minus 1. Now when we are talking about a single variance test, so I will just write that out, that a test of a single variance, let me come down. So basically a test of a single variance may be right-tailed, basically it can be right-tailed, or it can be left-tailed, or it could be two-tailed, right? So a test of a single variance, these can be three conditions regarding the test of a single variance. that it could be right-tailed, it could be left-tailed, or it could be two-tailed as well, right? So in the single variance, these three conditions actually apply out, right? So what is the test of a single variance? So test of a single variance assumes that the underlying distribution is normal. Like whatever distribution we are getting, that is normal. Fine. The null and the alternate hypotheses are stated in terms of the population variance. So whenever we just find out the null and the and the alternate hypothesis, so in that case we say out that we just like give out the answer, we say out in the terms in the form of the population variance or the population standard deviation. For the population variance and the popular deviation standard deviation formula, that we are already very much aware of it because we had already seen that into our previous videos, right? Next, basically, we are having regarding the test statistic. So, the test statistic is we have the formula that's n minus 1 multiplication s square upon sigma square, right? So, yeah, this dot which I had put on, that's a multiplication sign. It's not that any decimal point or anything like that. No, it's not like that, okay? Great. Now, next downside, we are having the value for n. So, the value for n, we are having that the total number of data. What about the S square? So for S square, we have sample variance. We have sigma square. So what about the sigma square? We have the population variance. Right. So now you may think of that S as a random variable in this particular test. So in that case, the degrees of freedom which we are having right here is df is equal to n minus 1, right? So our test of a single variance may be right-tailed, left-tailed, or it could be two-tailed as well, right? It depends basically on the condition, that what kind of values and what kind of conditions you are given out, and according to that basically it gets out decided that it is right-tailed, left-tailed, or two-tailed. Right, so hope I meet up this thing as well very much clear to you regarding the different types of tests, and even I just made out the things very much clear to you regarding the test of a single variance. So we'll be seeing up more topics in our new videos. This is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So now I'll be discussing about the summary of all the formulas which we had seen into this relevant and this particular topic, that was the chi-square distribution, right? So here now we go with the summary of all the formulas. So here it's my topic, summary of, and here goes the formulas, right? Yeah. This is what we are gonna study right today, and we're gonna take out a quick summary of the formulas, so that at the time of revision and all these things, these particular quick summaries help us a lot while dealing with the questions and while dealing with all of the things, right? Okay, so I'll be starting up here with the quick summary. So what I'll be doing is that I would quickly take out a new color from this particular place. Let's say it's this one, right here. So let's start out. So for the first thing, I'm just quickly going to discuss about the chi-square probability distribution. So the chi-square probability, the chi-square probability distribution, right? So for that, we are having the formula that's mu is equal to df, and we are having the formula that sigma is equal to under root of 2.df, right? These are the formulas that we are having out here for this particular probability distribution. Now let's move towards the topic, and that's the goodness of fit hypothesis test, right? Let me come down, get out some space for writing. Putting out a dot here, and yes, from here it starts out that it is goodness of fit hypothesis test. Okay, this is a topic, that's the goodness of fit hypothesis test, right? So the very first point goes here that use goodness of fit. Okay, instead of writing out the complete name, I would simply write or use this. Okay, use this test to find, whether our data whether a data set fits a particular probability, fits a particular probability distribution. Probability, and here goes the distribution. Okay, right. So this is what this particular goodness of fit hypothesis is used for. It's basically used for checking out this particular to find that whether a data set fits a particular probability distribution or not. This is what it is used for, right? So yeah. Okay, I will just make out a little bit of change here. Just let me quickly open out remove out this notification thing. 1 second. Yeah, right, here it goes. Okay, so yeah, goodness of fit hypothesis test. So in this test, basically use the test to find whether a data set fits out a particular probability distribution or not, right? This is what it is used for. Next, what we are having out here. So the second point, we are having the degrees of freedom. Let me come down here. That the degrees of freedom are number. So the degrees of freedom are number of cells or categories. Number of cells or categories minus 1. Right? This is what the degrees of freedom are. So degrees of freedom are number of cells or categories minus 1. Fine. Next, we are having the third point. Now, what we are having here. So the test is statistic. The test statistic is, what's the test statistic that we are having? So it's we have already seen sigma. Downside we were having k. Above we were having O minus E whole square divided by E, right? This is what we were having as a test of statistics. So test of statistics is this, putting out a comma and using out here that where O is equal to, we have the observed. O is equal to observed. Then we are having here values. Into the bracket, we will just put on the data, that's the data as well, right? So yeah. So this is about where O is equal to observed values and the data. And what about E? What we were having as a E? So E was my expected values. So here goes expected and here goes the values, right? And that's from the theory. So from, and here goes theory. Fine. So O is basically my observed values and E is basically my expected value, right? What about the K? We were having the K as well, right, into the formula. So K is it's the number of different data cells or categories, right? So K is basically the number of different data sets or the categories which we have out. Okay, fine. Coming down here, next we are having the point number 4, and the point number 4 is that the test is right tailed. The test is the right tailed, right? So yeah. These are some rules, these are some, you could say, a summary, a quick recap regarding the goodness of fit hypothesis test, right? Hope I am very much clear with this particular. Next, I will be moving forward with the test of independence, right? So here put the point and here goes the test of independence. Okay, right here. So what I'm going to first point which I have, that they use the test of independence. Use the test of independence to test whether two factors are independent or not. are independent or not. Right, so first of all, the test of independence is used to basically use the test for independence to test out that whether the two factors which are like they are independent or not. Right, now next point which we are having, the degrees of freedom. So here goes the degrees of freedom. So the degrees of freedom are equal to let me come down. So degrees of freedom are equal to, what are these equal to? These are equal to number of columns minus 1 into number of rows minus 1. So here goes number of columns minus 1, and next we are having number of rows minus 1, right? So yeah, this is the degrees of freedom, and that is equal to both of these particular things. Fine. Now moving next, we have the test statistic. The test statistic which we have for this is, so the test statistic is, we have here the sigma, here goes I multiplied by j in the bracket, and next I'm having O minus E whole square divided by E. Okay, the test statistics is this. Okay, where, now what are these all notations which I had put on? So I would just write on where O is equal to, it's the observed value. O is the observed value. Fine. What about E? So E is basically the expected value. It's the expected value. Okay, and what about the I and the J? So I is, okay, let me write it out. I is equal to the number of rows. Okay, number of rows in that table. So it's not, I do not think so to write out the that as the number of rows in the table. Okay, and what about the J? So J is basically the number of columns that we are having. So it's the number of columns. Right, so yeah, this is the formula regarding the test of independence for all of these particular things, right? Now what I'll be having next is that, let me just go down quickly a little bit here. Now what next thing regarding this particular, okay, it's the fourth point. So this particular test, the test which we are seeing, that is the test of independence. So the test is with the right-tailed. It's right-tailed. Okay, and next regarding the last point, that if the null hypothesis is true, then basically the expected number, the expected number which we have, that is, if the null hypothesis is true, then the expected number, that was E, right? So that E is equal to row total, in the bracket we were having column total, row total, column total, and downside we have the total surveyed. So total and surveyed, right? This is what we have right out here. So if the null hypothesis is true, so in that case the expected number, that's the capital E, that was we have used in the formula as well. So capital E was denoting out the expected number, right? So it's row total into column total upon total surveyed, right? So hope I am very much clear with this particular thing as well regarding the test of independence, right? So here we had taken the summary regarding the test independence and what was the above one that we had seen. So that was goodness of fit hypothesis test. Now we are left with two of the things, test of homogeneity, and the next which we are left out here with is the test of the single variance. So that will be seeing up in the next video. So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So we were discussing about the summary regarding all of these topics which we have studied. So we're discussing about the goodness of fit hypothesis test, Then we had taken out the summary of the test of independence, right? So now I'm moving towards to the next one, and that's the test of homogeneity. So this time I'm going to take out some new colors so that we are able to write out the things right here. Let's write it out. Next point, I am having here test of homogeneity. Test of homogeneity. Right? This is what we are going to discuss up right here. Okay. So let's discuss at the very first point that it is basically use the test for homogeneity. Use the test for homogeneity. Use a test for homogeneity to decide if two populations with unknown distributions have the same distribution as each other. Okay, this is what the test of homogeneity is first of all used for. So use a test for homogeneity to decide if two populations with unknown distributions have the same distribution as each other. Okay, now let me just come down here. What is the second point that we are having? So the second point is that the degrees here goes, yeah. So the degrees of freedom are equal to number of columns minus 1. Right, this is what the degrees of freedom are. So the degrees of freedom are equal to the number of columns minus 1. Moving towards the third point, we have the test statistic. The test statistic which we are having is, let me just quickly get out some space. So yeah, it is sigma I into j O minus E whole square divided by E. Right, this is the test statistic which we are having. So the test statistics is this. What are the O, E and Ij? So yeah, I hope you are very much clear again with that. O is the observed value, E is the expected value, I we have the number of rows, and J is the number of columns. So I'm not going to write that out again. Okay, right here. Let's move toward the fourth point. So yeah, this test is as well. So that I would write out that the test is right. Tailed. Right? Yeah, this is about this particular test as well. That this test is right tailed. Then we have number 5. So for the fifth point, if we have that if the null hypothesis is true. Again, let me just come down that if the null hypothesis is true, then the expected number that's capital E. Okay, then the expected number that is the capital E, it is basically equal to row total multiplied by column total and divided by total surveyed. So here goes the total and here goes the surveyed. Okay, so yeah, this is regarding this particular, that if the null hypothesis is true, then the expected number, that is E, which is equal to the row total, column total and the total surveyed. Okay, great. Now let me just come down here. So yeah, this was about the test of homogeneity. So in that case, basically we have one another thing, that the expected value for each cell needs to be at least 5. That's a minimum, right? That's a minimum, that it needs to be at least 5 in order to use out the goodness of fit, right? So this is basically about that particular one. Now next I am having the test of single variance. Let's see about the test of single variance. Next here I am having, I will just write out test of single variance. Test of single variance right here. Let's start it out. So basically we use this test, use the test to determine variation. So use the test to determine out the variation. So this is where we use out this particular test. So we use out this test to determine out the variation, right? I hope I am clear with this particular thing. Next, basically, what are the degrees of freedom? So the degrees of freedom are the number of, so the degrees of freedom are the number of samples minus 1. So degrees of freedom which we are having, that are the number of samples subtracted by 1. Now next we are having that the test statistic. So the test statistic is basically, now what's the test statistic that we are having? Let me just go down and write it out. So the test statistic is n minus 1 multiplication s squared. Right, is a test statistic which we are having. It is n minus 1 multiplication s squared divided by sigma squared. Okay. What are these values? So where n is equal to the total number of data, it is the total number of okay, let me write it out. Data, it is the total number of data. Fine. So where n is the total number of data. Next, what about next? So it is the s squared is equal to, that's the sample variance. So s is basically the sample variance. Okay. What about the sigma squared? So that sigma squared is the population. So it's the population variance. So variance. Right, so where basically these are the terms that we are having. N is the total number of data, s squared is the sample variance, and sigma squared is the population variance, right? Coming down. Now, okay, we have 4th point, right? So now 4th point that we are having, so it can be that the test, in this particular we do not have a condition that the test is only right skewed. So test may be left, okay, one second, maybe left, right, or, so the test which we are having here, it might be left, right, or it could be as well two-tailed. So for the above 3 we had seen that the test can only be right-tailed, right? So now it's not that case right here in this particular test of single variance. So here it goes that the test could be right, left, or two-tailed as well, right? Now let me just go above once. Okay, one second, right here, summary of the formulas. So yeah, these were the formulas that we have seen. So for the test statistics, we have goodness of fit hypothesis test. So for that, the test statistics is sigma k, in brackets we have 0 minus e whole square divided by e, right? Next, we are having that the test for the independence. So in that case, the formula for the test statistic is sigma I multiply j, in bracket we have 0 minus e whole square divided by e, right? Now next we are having out here regarding the null hypothesis. So null hypothesis is true, then basically the expected number is e is equal to row total into column total divided by total surveyed. Then we are having the test of homogeneity. So in that case you are having the test statistic, that is sigma I multiplied by j, in the brackets we have 0 minus e whole square divided by e. And then if I move towards the, if I move towards the null hypothesis, in that case if it is true, then the expected number which we could have is e is equal to row total into column total, okay, divided by the total surveyed. Fine. of single variance. Into that we're having test statistic as n minus 1 into s squared divided by sigma squared. And in that case the test might be right, left or two tailed, doesn't matter at all completely. Right. So hope I am very much clear with these particular comparisons, these particular formulas regarding all the four topics which we have studied under the chi-square distribution. Right, hope I made up these things very much clear to you. So now I'll be meeting with you in the next video. So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So now from today we are going to start out a new topic, and that's a linear regression and correlation. Let me quickly put on some heading right here. After that I will be discussing regarding this portal, okay? Right here, so it goes that linear regression and correlation. Okay, this is a topic now that I am going to follow up here. So right here, this particular one, and now it goes. Now basically first of all I'll be starting out with a very introduction, that's what it is and what it is completely used for. So okay, see, we have out a case here that professionals, basically sometimes professionals want to know that how two or more numeric values are related, right? Let's say you are having a numerical data or you are having some numerical sets. So into that case, sometimes professionals want to know that, okay, how are these numerical variables related, the numerical values, the variables which you are having, how are they completely related out, right? This is what they sometimes wanted to know. Example, let me take out. So basically there is a relationship between the grade on the second math exam a student takes. Okay, if there is if there is a relationship between the grade on the second math exam a student takes and the grade on the final exam, right? Is there a relationship? What does and how strong is the relationship? These are all the things which basically we need to know out. Let's say a student had given out the second math exam and a student takes out the grade, and basically what's the grade on the final exam as well. So this is what basically it's willing to know for basically wanted to know, right? Another example I could say that your income may be determined by your education, your profession, your years of experience and your ability, right? So the amount you pay a repair person for labor is often determined by an initial amount plus an hourly fee. Right? These are all the examples in which where can the regressions be used out, right? So basically here these are the cases where the regression can be used. Also in that case the type of data described in the examples, right, the examples which I had given you right above. So type of data which I had described there was the bivariate. Data. We often call it as BI. Okay, we often call it as BI. So bivariate data we often call it as BI. Okay, that's BI for the two variables. Bi means the two variables, right? So it's for the two variables only. So in reality basically statisticians mostly focus upon the multivariate data. So it's multivariate, and here goes the data. Fine. So the examples which I had shown you, that were the bivariate data. Bi means the two, right? And basically the statisticians completely see about the multivariate data. Okay, that means having the many variables, right? So this particular linear regression and correlation topic focuses upon the studying of the simplest forms of the regressions, right? Like the linear regression with one independent variables. We'll be seeing about the data that fits in a line in two dimensions. We'll study about the correlation. That what is this correlation for? It basically measures that how strong the relationship is, right? So these are all the things that we will be studying up here in this particular topic, that's a linear regression and the correlation, right? Now What I'll be doing is that I'll be taking you to the very first topic that okay, not like this. I'll be taking you to the very first topic that I am having right here, and that's the linear equations. Okay, yes, this is the topic. Okay, let's come down and studying about this particular thing. So I would start with the writing only that linear regressions, the linear regression for two variables, the linear regression for two variables is based, linear regression for the two variables is based on a linear equation, is based on a linear equation. It's based on linear equation with one independent variable. Okay, now the form which we are having here in the for linear equations form that we have out here, so it's y is equal to a plus bx. Y is equal to a plus bx. Hope many of you are familiar with this particular form as well. That's y is equal to a plus bx, because we get out these things in our very younger classes, right? We have already studied about these things onto our younger classes, right? So this is about the linear equations, that linear equations for the two variables. It's okay. Okay, how come this particular has been appeared? Let me quickly remove this out. Till the time I would not speak out, like I would not deny while speaking out. Okay, yeah. So linear equations basically it's for the two variables, right? We had already seen out the formula as well right here. That how is the formula and how is that completely applied out? Okay, 1 second, right, and fine. Now, let me just come down here, get out some space for me to write out and write here. Okay. Now I will be seeing about some more things. Okay, where what are the values of a and b which I'm having here. So I could just simply write out here that where a and b are constant numbers. Okay, where a and b are the constant numbers, right? The constant numbers which we are having. So that is the a and b. Okay. Now, I could mention out here that x is the independent variable. X is the independent variable, and y is the dependent variable, right? So basically we could mention out here that x is the independent variable and y is the dependent variable, right? So basically what we do, we basically choose out that which value we need to substitute for the independent variable, and then basically we solve out the dependent variable things and things related to dependent variables, right? So in that similar case, I just mentioned out here that x is the independent variable and what's the y is the dependent variable which we are having out here, right? So when we talk about the linear regression or correlation, so in that case two terms come. That first one is the bivariate data, that is bi, and the second one is the multivariate data, that's basically for the multiple variables. Now, when we talk about the linear equations, so in that case, the linear regressions for two variables is based upon a linear equation, okay, which has on a linear equation. That particular linear equation shall have about one independent variable, right? Y is equal to a plus bx. And where a and b are basically the constant numbers which we are having here, okay. What about x? So x is the independent variable and basic and y is the dependent variable which we are having. So it completely depends that what variable you set on as dependent and what variable you set as independent, that depends on you, right? So you completely to choose out a value to substitute for the independent variable and then solve out the dependent variable, okay. Hope I am very much clear with this particular thing to you as well, right? Now what I'll be doing is that, so here I'll be stopping up this particular video and we'll be meeting you in a new video with some new things regarding this linear regression, the correlation. Basically, we'll be continuing it, right? So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So today we're going to start out a new topic, a discussion of a new topic here in the statistics for data science, and that's F distribution and one-way ANOVA. So this is the topic, this is the particular topic now which we are going to deal, and this particular topic only we're going to study in the statistics for data science, right? So what I would just do is that let me start out with the introduction for this particular topic, that what was the need of taking out these particular things and giving out the introduction. What was the need of all of these things? Let's start off from that particular place, okay? Right here. So I will start out that there are many statistical applications in, you could say, in social science, in psychology, in business administration. So basically there are many applications of statistics in all of those particular fields, right? Now let's say I just take out an example that and basically we are having an environment and it is interesting knowing the average amount of pollution that varies in the several bodies of water. Okay, let's say this is particular one of the statistical analysis what I'm going to do out, that I just want basically there is an environmentalist and that person wants to know about, that interest is knowing about the average amount of the population pollution varies in several bodies of the water, right? This is what this particular person wants to know, right? Now, so in all of these cases, basically we'll be using out the hypothesis test, right? So for basically for hypothesis test, we involve out more than two average, right? And basically these are we basically analyze out more than two averages, right? Like statisticians have developed a method which is called as the analysis of variance, right? So that's completely the form of this ANOVA. So here it stands for AN stands for the analysis. So analysis. This O stands for of, or VA stands for variance. So yes, this is how this analysis of variance is. So F distribution and one-way ANOVA. Okay, this is what this particular one means out. Okay, full form of ANOVA, analysis of variance. Right. So this is the for a hypothesis test which basically have more than two averages. So in that particular case, this analysis of variance was the thing that was introduced, right, and that was developed. Fine. Now basically what we have, so in this particular chapter we are going to study out the very simplest form of the ANOVA, which is basically called as a single factor, or we call that as a one-way ANOVA. Okay, it's called as a single factor. I will just write that out. Called as single factor or one way ANOVA. Okay, so that is called as single factor, or it is called as a one-way ANOVA. Fine. So now basically we'll be studying about the F distributions as well, which is used for the one-way ANOVA. And basically this is the test of two variants, right? As I mentioned out that ANOVA means for the analysis of variances, right? So what I'll be doing is that here I'll be letting you know about these particular topics in detail in the further, right? So let's go ahead and study out first of all regarding, let me come down first of all. Okay, let me take out a different color here. One second, let's say right here. And now I'm going to start with the very first topic, and that's the one-way ANOVA. So one way, and here goes the one-way ANOVA. Okay, now onto that as well, I'll be discussing about the F distribution, F distribution, and one-way ANOVA. Okay. So into that particular, we are going to discuss about the purpose and the basic assumptions of the one-way ANOVA, right? Now let's get started out. So I will just simply take out one different color here so that it makes easier for me to go ahead and write out the things. So color I would be taking out from here at this place, and let's say this is the one, okay? Right here. So I'm going to start out with the purpose first of all, and after that we'll moving forwards, okay? So the purpose, what's the purpose? So the purpose, and let me take out a dark color. It's a little bit of, I guess, light one, right? Above one, I just need it out. So right here, okay, now it goes that the purpose of a one-way ANOVA. What's the purpose of a one-way ANOVA? So the purpose of one-way ANOVA test is to determine the existence, is to determine the existence is to determine the existence. Let me just go down from here. So the purpose of one-way ANOVA test is to determine out the existence of a statistically significant difference. So the purpose of one-way ANOVA test is basically to determine out the existence of a statistically significant difference, okay, among several group means. So this is the first and the foremost purpose of the one-way ANOVA test, that it is to determine out the existence of a statistically significant difference among the several group means. Okay. Now, next thing regarding this particular that this test actually uses variances. This test actually uses variances to help determine if let me go down right here, fine. So this test actually uses variances to help determine if the means are equal or not, right? So this is the one, I could say, one another purpose of the one-way ANOVA test, so that basically this test actually uses out what we use out here. So it uses out the variance and helps to determine if the means are equal or not, right? This is what, and this is where this is actually used out. This one is used for checking out and finding out the variances that will help to determine that the means are equal or not. Fine. So the complete purpose of the one-way ANOVA test is completely to determine out the existence of a statistically significant difference among several group means. So this test actually uses the variances to help determine that if the means are equal or not, right? Now, as I mentioned in the starting as well, that for the one-way, for this particular term that we are having ANOVA, so the full form for ANOVA is analysis of variance. So from there only I could just understand and I could just use it out that this particular test uses the variances to help to determine the means that are equal or not. So whenever we just want to determine out the means that that means which you are having that are equal or not. So into that particular case, we use out this ANOVA test. Even from the name only, it suggests out that particular thing regarding the variance, right? So it is as well known as a single factor, or you could call it as a one-way ANOVA. Anything actually works out here. Single factor or one-way ANOVA. Right. So hope I am very much clear regarding this particular thing regarding the F distribution and the one-way ANOVA. Now, we have several things to watch here in this particular one. We have some assumptions and we have many things to go ahead. So that all I'll be discussing with you in the further videos. So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So as in the previous video, we had discussed about this particular ANOVA thing, right? That what is this ANOVA and what are the things that we are having right here. Now, today I'll be taking you to the assumptions, that what are the 5 basic assumptions that needs to be filled up. What are the assumptions that actually need to be filled up here whenever you are using out the one-way ANOVA. Okay, so let me just go down here for a while. And right, let's start out here. So I would simply take out a new color so as I could just start writing out the relevant things onto this particular place, and this time it goes one like this right here. So I would mention out that in order to perform a one-way ANOVA, in order to perform a one-way ANOVA, in order to perform out the one-way ANOVA test, there are few basic assumptions. Okay, so there are few basic assumptions. So I would just mention that out here as well, assumptions, right? So yeah, in order to perform out a one-way ANOVA test, there are few basic assumptions that need to be followed out, that needs to be fulfilled. So the very first one that we are having is that each population, so yeah, so each population from where a sample like this, right? So each population from where a sample is taken, is assumed to be normal. Okay, so each population from where a sample is taken is assumed to be normal. Fine. Now moving towards the next we are having the second point. So the second point is that each sample is randomly selected and independent, and here goes independent. So whatever the sample we are taking, so first of all that's a randomly selected, and next we are having that it is independent as well. So whatever the sample you choose out, that's a randomly selected sample and even the independent sample, right? This is the second point. Moving toward the third one, we have the population are assumed, I will just write that out. Let me just go down here for a short while. Great, so the population are assumed to have equal standard, deviations for variances, right? So the population which we are having, that is assumed to have equal standard deviations for the variances, right? Moving towards the number 4, that's the factor is the categorical variable, the factor is the categorical, one second, let me go down. So the factor is a categorical variable. So yes, this is point number 4. And next point that we are having, that's the point number 5. So into that we are having that the response is the numerical variable. So here we go with the variable. Great. Now let me quickly explain you all of these 5 assumptions that are written out here. Now very first thing that needs to be explained up here in this particular case is that whenever you are performing out a one-way ANOVA test, right? So in that case, there are these few basic assumptions that need to be followed out, right? The very first assumption that needs to be followed out is that each population from where a sample is taken is assumed to be normal. So from wherever you are taking out the population, right? Each population, from wherever you are taking out this particular population and where a sample is taken, okay, from which the sample is taken, so that is assumed to be normal only, right? Hope I am very much clear with this particular thing. So the population from where a sample is taken is assumed to be normal. Moving towards the point number 2, we have that each sample is randomly selected and independent. So what are the samples you are having that are first of all randomly selected, and second one is that these are independent, right? So randomly selected and the independent samples you are having out. Next, moving toward the third, we are having that the population are assumed to have equal standard deviations for variances. So the populations which are basically assumed that they have the standard deviations for the variance. So we just assume this out this particular thing, that whatever the population you are taking, okay, that has equal standard deviations for the variance. So all the standard deviations are equal for the variances whichever you are having, and for whatever the population you are actually assuming that. Fine. Next we are having that the factor is the categorical variable. Okay, now here when you go with the one-way ANOVA test, so in that case we have two particular things, that's the factor and the second one is the response. So if I just talk about the factor, so that is a categorical variable. Now what's that categorical variable called? So okay, categorical variables are the type of variables in which what you are having the characters, you're having out the words, you're having out the alphabets. So what are the variables are there into which you are storing some you could say some characters or some words. In the particular case, those are called as the categorical variables. Okay, now whenever you are using out the numerical variables, so in that some sort of numerical value has been associated, either it could be integer or it could be float, that doesn't matter out, but what matters is that it would be numerical variable. So the response which you are having, basically that is the numerical variable, right? Factor goes in the field of a categorical variable, right? And response goes in the field of the numerical variable. So when we talk about the ANOVA test, so in that case what we do, we basically determine out the existence of a statistically significant difference among several group means. So we are having several group means, and among that we find out the existence of the statistically significant difference. This is what we do right here, right? This test completely use out the variances to help determine if the means are equal or not. So in this particular case, we simply use our different variances that helps us to determine that whether the mean are equal or not, right? So in the same case only, the last point is also mentioned one right here, that the populations are assumed to have equal standard deviations for the variances. This is the reason this particular point is mentioned out, that the populations which we are having, those are assumed to have out the equal standard deviations for the variances, right? So hope I am very much clear with this particular thing as well, that for the population that from where sample is taken is assumed to be normal, and the sample is randomly selected and independent. Populations are assumed to have equal standard deviations for the variances. The factor is the categorical variable, the response is the numerical variable. Fine. And ANOVA as well means out this particular same thing only, that's known as analysis of variance. AN for analysis, O for of, and VA for variance. Right? So hope I am very much clear with this particular thing regarding the F distribution and the one-way ANOVA. So now we'll be meeting up in the next video with some more things regarding the same topic, that's the F distribution and one-way ANOVA. So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So as discussed previous, we had seen about the one-way ANOVA and the F distribution things, right? Now today I'll be taking you towards the null and the alternate hypothesis which we have out here. So the topic of discussion for today is null and alternate hypothesis. Okay, so this is the topic of discussion for today. So let's go ahead and put on some of the things regarding the null and the alternate hypothesis. Let's understand out the things. Okay, if I start on with the null hypothesis, so yeah, right here. So the null hypothesis is simply that is simply that all the group population means are the same. Right, so null hypothesis is simply that whatever the group population means we are having, all of them are same. If I talk about the alternate hypothesis, so the alternate hypothesis, let me just go down and check out this particular, get up some space for writing. Great. So the alternate hypothesis is that at least one pair is different. So the alternate hypothesis is that at least one pair of means is different, right? This is about the alternate hypothesis. So first of all, let's quickly clear it out regarding null and the alternate hypothesis. Null hypothesis is simply that all the group population means are the same, right? That what are the group population means we are having, all of them are completely same in the null hypothesis. Now, if I talk about the alternate hypothesis, so in that case, at least one pair of mean is different. Okay, great. So, how we do denote out these particular things for the mean and the alternate hypothesis? So, this is basically the null hypothesis, H naught. Okay, and here we have it in the form of mu1, that's equal to mu2, that's equal to mu3, that's equal to up till that's equal to mu k, right? Because I had just mentioned this particular thing out because I said you that into the null hypothesis we have the everything right here in the same, right? We have all the values are same here. So in that case I just mentioned out h1, h2, mu1, mu2, mu3 and mu k, these all are equal. Now if we talk about the alternate hypothesis, that is HA. Okay, so in that case we mentioned out that at least two group of means are not equal, right? So into that particular case I could simply write it out here that okay, it's not like that, it's at least two of the group means that's the mu1 comma mu2 comma mu3 comma up till that's the mu k are not, let me just go down, are not equal, right? This is what we have studied about the alternate hypothesis. So the same thing I just simply mentioned out are these particular cases. Now we have some graphs here as well onto these both of the hypothesis, the alternate and null hypothesis. So what are they used for? So the graphs which we have out here, okay, so the graphs help in the understanding right here. Okay, so the graphs help in the understanding of the hypothesis of the hypothesis test. So the graphs help in the understanding of the hypothesis test. Okay, so in that case let me just go down here for a short while, and what I'm going to do is that I'm going to just okay, 1 second, what has this happened, 1 second. Right here, okay, Ragit, fine. So of the hypothesis test, right? So I could mention up here that in the basically we'll be making out some graphs. So in the graph basically we have some same distributions of the null hypothesis. So whenever those values are completely same, so it is said that all of those three are same, so it is said that a null hypothesis is true. Okay, whenever we are having the same distribution So in that case, we say that out the null hypothesis is equal to true. And in the case where there is no such thing is happening, like where there is all the three variances are not similar, or the three populations or the same distribution is not done. So in that case, we say that the null hypothesis is false. So in that case, it goes on to the alternate hypothesis part, right? Yes. Right. So that is okay. So what I would do is that first of all, let me quickly make out the graph for the null hypothesis, then I would let you know. So, okay, let me get out some space as well right here for writing that out and for making that out. So here goes the draw, and I would just simply take out some squares like this. Okay, it's like this one. Next as well I would be having, and this one is the 2. Okay, one more thing right here, that please assume that all of these three are equal, because I won't think so that I'll be able to make out all of these three as same and similar or equal to each other, but they will be equal, right? Please make sure to remember that out. Okay, this is done. And next as well, this particular third one goes like okay, not this, like it's like this. I could assure, right, okay, this is okay. And this is basically a kind of a box plot which we are making, this as well, box plot, and this as well, right? Now basically these are three different boxes that we are having out here. So I will just fill up this box as well with some or the other color, and till a while I would just let you know as well about these. Now after this, what I'll be doing is that I'll be making out the one line here, and that will be representing out the mean of these boxes. Okay, what are the boxes we have made out? It will be representing out the mean for all of those three boxes. So particularly inside those boxes, what will be happening? Whatever the mean we are having, I would make out the line at a similar place. So whatever the mean we will be having, all the means will be same for all these boxes, are kind of a box plots which I had made out. You could say just anything regarding that particular. Okay. So into that particular case, it would show us that yes, the points which we are having and the means which we are having for all of those threes, these are completely equal or completely similar to each other. Right, so when I just make out the mean, see, whenever, okay, in box plot, what we get to know in the between, that's the mean only, right? The mean we get to know out regarding that particular one. So when I make that out as similar, so in that particular case, it absolutely would be that yes, the mean is completely similar to each other. Let's say I just put on my line like this right here, second line as well here, and third line as well here. Now, into this particular case, I could say that H0 is true. I could simply mention this, that it is true. Why? Because all means are same, right? I could simply mention out this particular thing, that H0 is true here, and the quick reason for that particular thing was that all the means which we are having right here, all the means are actually same, right? So this is the one of the cases that goes here. So what are the graph we have made out here for the hypothesis test understanding? So in that case, all the three populations are having the same distribution, right? Are having the same distribution if the null hypothesis is true. So the variance of the combined data is approximately the same as the variance of each of the population. So variance for this combined data will approximately be equal to the variance of the single box plot for single plot as well, right? So hope I made up this particular thing very much clear to you regarding that what are the means, how, and what about the null and the alternate hypothesis here at this particular place, right? So here we saw about the this particular null hypothesis. After that, we have the alternate hypothesis as well. So that I'll be taking you in the next video. So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So into the previous video, we had discussed about that null hypothesis with the help of some graphs as well in a very detail, right? So today we'll be discussing about the alternate hypothesis in a detail. So we'll be discussing that when we say that it is an alternate hypothesis. So let me quickly take out a color here and let me draw out, okay, not right here, let me draw out three boxes at this particular place, somewhat like this. Yes, okay, so I would just not here. This one goes as the first one. So here goes my second box as well. Okay, and let me just quickly take out one more particular box right here. And here it goes the third box for me, right? So yeah, all the three boxes I have simply made out. Now here we have the option, I would remove this out. Here we have the option for making out the box plot. As I mentioned that I'll be distributing the things in the form of a box plot right here. So okay, one more second. This box need not to be made up at this particular place. I'm so sorry. I would again take out the color because here we are describing out the alternate hypothesis. So in the alternate hypothesis, all the boxes are not similar to each other, right? That we have already discussed about, right? So yeah, that is okay. And the next one goes up at this particular. Okay, the same one has been okay displaced. Fine. I would do one thing right here. I would simply take out the eraser right here, and I would simply make out the another box at this particular place. And next goes the next one as well, like this, and it would be coming at this. Okay, yeah, this is sorted, right? This is how we just get out for the null hypothesis, the alternate hypothesis. What we studied for the alternate hypothesis, that whatever we just take out here, everything basically whatever is we just take it out here onto this particular alternate hypothesis. So all the values which goes up here and which we have, these are if these are not equal, if these are not same, right? So in that case, what we mention out, we say that the null hypothesis is false. We do not say that alternate hypothesis is true or anything like that. No, we don't do out that particular thing. We simply convey out that the null hypothesis is false in this particular situation, right? So in that particular case, simply that means that we are just having out a distribution, we are having out a sample, and onto that we had checked that whether this particular is having the null hypothesis or the alternate hypothesis. So if the alternate hypothesis is not there, sorry, the null hypothesis is not there in that particular case, so we simply mention this out, that the null hypothesis is false at this condition. If you watched out my last video, so onto that particular, what I had done, I had already defined out, I had already made out one of the box plots for the previous one, right? I had already done out that particular thing. So onto that, I had told you that when all of the ones were having the same mean, right? All the boxes which we were having, all of those boxes were actually having out the same mean. Same means that it is basically the alternate, sorry, null hypothesis. Now, if I just draw out the lines up right here in the between somewhere like this. So here could I say that the means are same? No, it's not actually same, right? It's not same, right? So into that particular case, we just say out that the means are not same. And if I just need to write this out, so I would say that H naught is equal to false. We do not write that HA is equal to true or anything like that. We simply write that like let's say we have H naught, that's my null hypothesis. So we simply say out that the null hypothesis is false in this particular case, right? So I would now just let you know the complete description of this particular one which we are having right here for the second one. Okay, so let's go back and let me just come down. So let me get out some space for me to write out the things so that it's clear to you regarding all the things which we have studied out, right? So I would just mention out that in null hypothesis, okay, not in, it's if. So if the null hypothesis, is false, basically the null hypothesis which we are having, if that particular goes here as false, so in that case what we say out, let me just go down. If the null hypothesis is false, in that case then the variance of the combined data is larger, which is caused by the different means which I had shown you in the previous plot which I had made out. Right, so if basically null hypothesis is false, as I mentioned out that whenever the means are not similar, so in that case we just simply mention out that a null hypothesis is false. We do not put on that it's true or anything like that. We simply put on that a null hypothesis is false. So in that case, what happens that then the variance of the combined data, like what are the combined data we are having? So the variance of that combined data is larger, okay, which is basically caused by the different means. So when all the means are actually similar to the data which we are having, so in that case we say out that the variance of the combined data is like similar, okay. But when we are having out the different means here, when we are having out a different means, so in that case we say out that the null hypothesis is false, then the variance of the combined data is larger, which is caused by the different means, right? So which is caused by the different means. So in that case, the null hypothesis is false. Let me go above and show you out the things. 1 second, right here. So for here, when we had made it out for the 1 second, here the null and hypothesis alternate. So the null hypothesis is simply that the group population means are the same. So what are the group population means we are having whenever it is same? So in that case we are having out the null hypothesis. And when the one pair at least at least one pair of the mean is different. So in that case we say out that it is the alternate hypothesis. So see, for the H0, that's my null hypothesis. All of these particular values which we are having all are same, right? And for HA, that's my alternate hypothesis. So we have that at least two of the group means are not equal. So the graphs basically which we are having that help us in understanding of the hypothesis test. So the one which we have made out here. So onto these the middle line which are actually right here. So these are displaying out the mean. Okay, these are displaying out the mean. So we are able to actually see that the mean which we are having here, that's completely similar to all of the three plots of all of the three box plots which we are having out here. So in that particular case we say out that the H0 is actually true. We can simply say that the H0 is true, and if the H0 is true, so in that particular case, okay, 1 second, if the H0 is true, so in that particular case all the means will absolutely be similar to each other. Right, next we are having, I had made out this particular plot for the alternate hypothesis. So when I talk about the alternate hypothesis, or so in that particular case I could simply mention it out that all the means which we are having onto these plots that are not equal to each other. So above when they were equal we wrote out that H0 is equal to true, that's the null hypothesis is true. Now here we'll be writing out that H0 is false. It means that the null hypothesis is false right here, okay. So if the null hypothesis is false, then the variance of the combined data is larger, which is caused by the different means. So whenever the hypothesis is false, in that case the variance which you are having of the combined data, that is completely larger, and that particularly is caused by the different means which we are having out here, right? So hope I am very much clear with this null and the alternate hypothesis to you very much regarding that what are these null and alternate hypotheses and how are these, what are these completely known as, when are the conditions true and when are the conditions false, and everything. Right, so this was one of the more important topic, one of the I would say important topics in this particular ANOVA. I would just remove this out. Right, this was one of the important topics in the ANOVA, so that we had already covered out. So now we'll be covering about some more topics in the further videos. So this is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So now basically we are going to learn about the F distribution and the F ratio. So what I'm going to do is that let me just quickly put on the heading, that's the F distribution. So here goes the distribution, and here goes the F, and here is the ratio, right? Yes, this is what we are going to learn today, that regarding the F distribution and the F ratio, okay? So now let me quickly take out the new color here so that we can proceed on with the basically writing out the things, right? So okay, let's start up. So I will just write out here that the distribution used for the distribution used for the hypothesis test is a new one. So yeah, basically for the distribution used for the hypothesis test is new, and for in that basically we have the we used out the hypothesis for the distribution. So basically it is called the F distribution. It is called the F distribution. So yeah, the distribution which is used for the hypothesis test is a new one, and it is called the F distribution. So right here I mentioned about the F distribution and the F ratio, right? So in that similar case, F distribution is the one which I mentioned out, that this is the distribution which is used for the hypothesis test. That is a new one. Okay, great. So here I mentioned of those particular things. So we have the what is that F statistics. So F statistics is a ratio. You could call it as a function as well. So I would just come down here. So I will just mention that particular thing as well. So here goes that the F statistic is a ratio. Okay, so yes, the F statistics is a ratio, right? Now, basically there are two sets of degrees of freedom. Okay, one for the numerator and one for the denominator. So completely I will just mention out that particular thing as well, that there are two sets of degrees of freedom. So basically there are two sets of degrees of freedom. One for the numerator, and I would come down, and other for the denominator, Fine. So yeah, here we have the two sets of degrees of freedom. One is for the numerator and the other one is for the denominator. Now let me quickly take out an example here. Okay, so here goes for example. Fine, let's see that what's the example here. So example is that, for example, if F follows an F distribution, one second, like this right here. So okay, now basically if F follows an F distribution, so F distribution and the degrees of freedom the degrees of freedom for the numerator and the degrees of freedom for the numerator are 4. Okay, one second, are 4, and the degrees of freedom and the degrees of, one second, let me just get out some space. So the degrees of freedom for the numerator is 4, and the degrees of freedom for the denominator are 10. Okay, so degrees of freedom for the numerator are 4 and the degrees of freedom for the denominator is 10. So in that case we say that, then F is approximately equal to capital F, and here goes 4, 10. Okay, so yeah, this capital F is approximately equal to this F, and in the downside it comes the numerator comma denominator. So numerator is the 4 and the denominator here we have is the 10, and we just get that out right here. Right, so yeah, this is how this particular has been done. Now here we have some note to be followed out, so let me just go down and let you know that particular thing as well. So here comes the note that we are having out. So the note goes that the F distribution, right here. So the F distribution is derived is the F distribution is derived from the students T distribution, right here goes the distribution. So the F distribution is derived from the students T distribution. Next here we have one-way ANOVA. One-way ANOVA. Okay, that's ANOVA. Right here. So the one-way ANOVA expands the t-test for comparing more than two groups. One second, let me just go down. So the F distribution is derived from the students T distribution. One-way ANOVA expands the t-test for comparing more than two groups. Right? Now what's the scope? So I would mention that out, that the scope of the derivation is beyond the level. Right, so yeah, okay, one second, I would just remove this out because the sentence is not to be mentioned out. That I would let you know afterwards. Okay, so let me again take out a color right here. Fine. Right here. So the notice that the F distribution is derived from the student's T distribution, and the one-way ANOVA expands out the t-test for comparing more than two groups. Okay, here goes the groups as well. For the more than two groups, right? So one-way ANOVA expands the t-test for comparing more than two groups. Fine. Right. So let me just go above and go ahead with this F distribution and the F ratio. So for the F distribution and F ratio, the distribution used for the hypothesis test is a new one. Okay, it is called the F distribution. Next, okay, one second. Right here. So for example, basically if F follows an F distribution and the degrees of freedom for the numerator are 4 and the degrees of freedom for the denominator are 10. Then in that case we say out that F is approximately equal to capital F, and in the bracket it goes like 4, 10. Right, what's the note that we are having? So the note is that particularly the F distribution is derived from the student's T distribution, and the one-way ANOVA expands the t-test for comparing more than two groups. Right, so hope I am very much clear with both of these statements which I have mentioned up here regarding the F distribution and the F ratio. Now basically we have that how we calculate out the F ratio. We have two estimates of the variance. So that I'll be discussing up in the next video. This is all for this video. Till then, thank you and take care. Hello everyone, my name is Shambhavi. Hope you all are doing well. So now what we are going to learn is that we're going to learn about how to calculate out the F ratio for the two estimates of the variances are made. So I'll be writing out and we'll be going to calculate the F ratio today. That's how we can do that out. Okay. So let me write that. So here it goes to calculate. One second. Let me write that correct only. So to calculate the F ratio, to calculate out the F ratio, two estimates of the variance are made. Two estimates of the variance are made. Okay, so to calculate the F ratio, two estimates of the variances are made. Fine. Now, basically, first one what we have, and before that, let me choose out a new color here for writing out, and fine here, and the number one. The number one goes here like that. Variance between the samples. Okay, so number one is variance between samples. Okay, the very first one which we have out here. Now, we'll be discussing about some things between the variance between the samples. Okay, so yeah, here I go that an estimate of sigma square, that is the an estimate of sigma square, that is the basically variance, that is the variance of the sample, means, that's the variance of the sample means multiplied by n, okay. So the variance between samples means that an estimate of sigma square, that is the variance of the sample means multiplied by n, right? Basically, next 1 second, let me get out some space for writing out here. Fine. Next we have that if the samples are different sizes, okay, basically if the samples are different sizes, then the variance between samples is weighted to account for the different sample sizes, Let me just go ahead above a little bit and revise that particular variance between samples. So it is an estimate of sigma square, that is the variance of the sample, means multiplied by n. Okay. Now, if the sample are different sizes, then the variance between samples is weighted to account for the different sample size. Right, so I hope I am very much clear with this particular thing. Then in that case, we have one more thing to mention out here, that the variance is also, 1 second, let me get out some space. The variance is also called variation due to treatment or explained variation. So the variance is also called variation due to treatment or the explained variation, right? So yes, this was about the variance between the samples. Now, next we are having the second one, that's the variance within the samples. Variance within samples. Now let me just come down here. Okay, fine. Variance within samples. So it is an estimate of sigma square, that is the average of the sample variances, Now, when the sample size, 1 second, right? So when the sample size, okay, so here we are having that when the sample sizes are different, are, so when the sample sizes are different, so in that particular case, the variance within samples, the variance within samples are weighted. Okay. Then in that case, the variance is also called as, I will just write simply like variance is, let me get out some space, and in that case variance is also called as variation due to error or unexpected variation So in the variation within the samples, what happens that an estimate of sigma square, that is the average of the sample variances when the sample sizes are different and the variances within the samples are weighted. So variance is also called as variation due to error or unexpected variation. Okay, so this is where this variance within samples actually meant. So these were the two estimates how you could found out the F ratio. Okay, variance between samples, and second one is variance within samples, right? So hope I am very much clear with both of these things in regarding about to how to calculate out the F ratio. Two estimates of the variances are made, right? So in this particular case, above we had seen about the one, that is the variance between samples. So that was estimate of sigma square, that is the variance of the sample means multiplied by n, right? And when I move towards the variance, variance within samples, so it is an estimate of sigma square, that is the average of the sample variances, right? So hope I am very much clear with both of these things. Now we'll meet you in the next video with some more new topics. So this is all for this video. Till then, thank you and take care.